All right. Can you please just put in the chat box if you can hear me? Yes. Okay, great. Thank you. All right. So let's see if we have the presenters today. Do we have Ruin in the room? Okay, great. Awesome. Do we have Yalong? Yes, great. Awesome. And we have Maryam and about the fourth presenter, Chuan. Yes, we have also Chuan as well. Awesome, great. So then we can actually start the next session. Thank you everyone for joining this session. I'm Ellie. I'm the Senior Lecturer of Transport Engineering at the University of New South Wales, Sydney, Australia. And our tech support staff today is Maryam. Maryam is a PhD student. She will also present her research today. So in this session, we have 6 presenters and only 2 hours. So the good thing is the last 2 presenters, we have the recorded video, so we make sure that we don't run out of time. So in terms of like the time management, please, I request all of the presenters to complete your presentation in 20 minutes. And if you can even like finish in 15 minutes, that would be great because there could be some Q&A time for us. Please use the chat box to post all of your questions, thoughts, similar research you're doing, any recommendation for the presenters. And also would appreciate if the presenter introduce themselves in the beginning of the session, which stage of PhD they are, or if they have already graduated, what's their title, and yeah, just a very brief introduction to get to know each other. So with that, then I can hand it over to Ruin. Ruin, would you like to share your screen so I stop sharing?
Hello, I tried to send request for. Oh, okay.
Yeah, the screen is loading.
Yeah, wait a minute. Is it okay now?
Yes, it is okay. Yes.
And
So
also,
I hand it over to
my
you.
voice is.
Please introduce yourself. Very looking forward to hearing from your research.
Wait. Maybe. Hello, everyone. My name is Ruin Fatimah. I'm from Southwest Jiaotong University. I'm PhD student in here, and my major is logistic engineering. Today, I want to present about the reducing container terminal distribution time through the SLP-based layout redesign and AnyLogic simulation. In here, I have a case study in New Priok Container Terminal and NPCT1, Jakarta. The main focus of this study is container terminal efficiency, particularly how the spatial arrangement of the terminal area can influence distribution time. In simple terms, this research asks whether a better layout can help container move faster inside the terminal and whether that improvement can be tested through the simulation. Before discussing the technical part, this is the Indonesian map. We can see Indonesia located between 2 continents, in Asia, between Asia and Australia, also between 2 major oceans, Indian Ocean and Pacific Ocean. Because of this position, maritime transportation play very important to role in connecting regions, supporting trade and maintaining logistic flow. In this context, port and container terminal become strategic logistic nodes. When terminal operations are inefficient, the impact is not only felt inside the terminal, it also affects the truck movement, vessel schedule and delivery reliability. Therefore, improving terminal operation is highly relevant in Indonesia. This is my background and research motivation. The background of this study starts from a practical problem in container terminal operation. Container terminals support international trade, but they often face operational delays due to congestion, long travel distance, and inefficient internal movement. Jakarta Port is used the case study because Jakarta is the one of the important container terminal in Indonesia. Also, is like the rank number 26, the busiest port in the world. So in Jakarta, this port it handle large container volume and support modern vessel operation. So in the methodology, this slide show the research framework used in the study. The workflow begins by defining the system boundary. In this case, Jakarta Port. I am divided to 5 main functional area or layout analysis. After defining this area, operational data are collected. Also after that, this include the throughput, truck movement, inter-area flow data, and also the next step is building the inter-area flow metric, which show how strongly each area interact with others area. From these metrics, the activity relationship chart, or we can say ARC, activity relation chart, is constructed. The ARC converts quantitative flow intensity into qualitative closeness rating, such as A, E, I, O, and U. After that, after we get the SLP gate layout, based on ARC closeness priorities, finally the original layout and the redesign layout we compare using the AnyLogic. This is my research aim, scope, and contribution. The main aim this study to assess how SLP gate layout redesign can reduce container terminal distribution time by redesign the NPCT1 layout using SLP and evaluating improvement through the AnyLogic simulation. The study focused on the terminal layout, inter-area movement, and time-based performance. It does not redesign the interport system, but focus on how the arrangement of the key terminal area can influence container movement. In this study has 3 contributions. First, applied decision support contribution is the combination of flow-based ARC, SLP guide, and AnyLogic simulation into the traceable workflow. This is explain the analytic logic of the study. The process begins with operational flow data, including through data, truck trips in the area flow and in area in Jakarta Port. Then after that, after we get the ARC, the step important is decision layout with the logic. In other words, the layout is not changed but intuition, but based on the strength of operational relationship.
Go here.
Also in this slide, this present the calculation logic use this study. I will explain briefly because it's not purpose here, not focus into mathematical complexity, but to show how the layout decision traceable and systematic. And in here, after we get the throughput data and everything, we get the ARC, activity relationship chart, like A is absolutely important, unimportant, ordinary, extraordinary, important, and after that, we can see like in A, if A, they have like 4 line like this, we can see in this red line means this is like trial and error. If the red line like this and or have the conjugation, it's not effective. So this is the best trial and error. There is no conjugation or like move to other place. So in this slide, let's compare the original layout. This is the original before the A. The original B is like proposed SLP. The original represent the initial specimen arrangement and of the terminal area. And this comparison is important because it shows what actually changed the layout. Redesign aims to place high flow and high priority. If we can see like what this is like I have 1, 2, 3, 4, 5. This is like this like 1 if for get office, 2 for export area, 3 for import, etc. So in this 4 prime mover area, so just for moving, this is just simple things for we just need moving the prime mover area so we can see like how distribution time it will be like more efficiency. So after I change the layout from the original to SLP, and after that I apply in AnyLogic, we can see the distribution time from original layout for import. They have make a reduction 18.85%. Also for export, this 33.6%. This we can see the result indicate that in this case, the designer like out can improve time-based terminal performance. The improvement is stronger for export movement, which suggests that export flow may be more sensitive to spatial arrangement in this case. So this is the discussion. The finding has several practical implications, but these should be interpreted as case-specific result rather than a general prescription for all terminals. Operationally, the SLP layout helps improve proximity between high flow area. This can reduce unnecessary internal movement and support smoother container distribution. From a managerial perspective, the framework can support evidence-based decision-making, terminal manager, operational flow data, ARC analysis, and SLP redesign. This study also has wider relevance for terminal planning, port, and development. However, future research can improve the model by using more detailed operational data, such as yard bulk, actual travel path, and multi-period flow data. To conclude, this study integrates ARC, systematic layout planning, and AnyLogic simulation to evaluate redesign at Jakarta Port. The results show the SLP developed layout can reduce distribution time. For import is 18.85% and for export 33.6%. This suggests the layout planning can provide practical decision support for terminal, while the redesign layout should be understood as one improved candidate because in here the case study just in Jakarta, we cannot say it will be we can use in the other terminal too. So this is my limitation. So yeah, thank you so much for maybe it's just part of my PhD research. So thank you so much for listening me.
Awesome, great. Thank you, Rin. So let's see if there's any question. Very interesting presentation. Ryan, which year of PhD you are at?
Sorry, Ellie.
Can you hear me?
Your voice is so low.
All right. Let me just. Can you hear me now? Okay, it's good. So, Rin, which year of your PhD you are at?
No, it's my third year.
Your third year, right. So, what's your plan for extending this research? And my question was basically more in terms of the impact for the sector or for the society. do you have any plan for extending your research?
Oh, I will extend like now it's just distribution time, but for the social maybe I now I try to for from SLP can there is impact or not for reduce the carbon dioxide. So not just distribution time, also for the CO2 carbon dioxide reduction.
Right. Yes.
So
And so in terms of like disseminating the findings of your research for the industry, what's your plan? Because nowadays we see lots of published journal papers. And in terms of like really the impact, the translation of these research, I'm just interested to know that what is your plan for disseminating the findings of your research to the industry and to basically society so that it has more impact?
Yeah, actually, unfortunately, now I'm start to not just for journal. I'm not just because this is just one port. So I want know like if I compare with other port, if there is like have impact or not. There is like my hypothesis for SLP is right or not. So maybe for if I can upload the journal, it can be like more how to say it in English. It will be like we can see like oh SLP is not just in Jakarta but in other ports too. So it will be like effect to more it's because as I know SLP is not the new method, but with the simple method we can make for the society and everything reduce the carbon monoxide, reduce
Yes.
the time for distribution and everything.
Yes, yes, great. Ruin, that's my second time that I'm listening to your presentation. The first time you presented in TLOC conference in Shenzhen last month. I asked a
Oh,
question.
we meet it, yeah.
Yes. So I asked already
Yeah,
my
this is
questions in Shenzhen. We have one question from the audience, and we don't have the name. It appears as Zoom user one, but the question is, why did you use distribution time as the main KPI?
so because distribution time. Thank you for the question. The no name distribution time is because it directly reflect how long the container movement in take inside the terminal. So since the purpose the study evaluate the layout redesign, so we can see distribution time is reduction or not, something like that.
Okay. Okay, awesome. So just be cautious of time. Thank you so much for your
So yeah,
presentation.
so thank you so much. If have question, maybe you can ask me in this email. Thank you so
chat.
much, Ellie.
Yeah. So please just
So happy see you
also leave.
again.
Yeah. So leave your comments in the chat box. Yes, same. And I'm basically looking forward to see more progress on your research.
Thank you so much.
So the next presenter is
I will
Yalong.
stop.
Thank you. So Yalong is, I assume that you are a PhD student at the University of Hong Kong under the supervision of Professor Szeto, Yuen. Yalong, please start sharing your screen. So Yalong, sorry for my bad pronunciation. Yalong will present a research on multi-port continuous Berth allocation problem, a mathematical model and heuristic algorithm. So we have your audio and video, and yes, we also have your presentation.
Can you see my screen?
Over to you. Yes, we can see it. Over to you.
Okay. Just how can sorry. I try it again. Maybe I use the slides.
Already.
Sorry.
But yes, try again.
Okay.
Yes.
Okay.
Okay.
Okay. I'll
Over
start.
to you. Yes, please.
Okay. Hello, everyone. I'm very happy to give the presentation on our previous work titled A Multi-Part Continuous Burst Allocation Problem. And my name is Yalong, the presenter today. The contents include 4 parts: the background, the methodology, results, and the discussion. Let's start with the background. Driven by the ongoing growth of the maritime transportation, the severe port congestion has caused the massive delays and financial losses. Physical port expansion is capital intensive and geographically constrained. Compared with it, the technical optimization would be more acceptable. To achieve this, the port operators are encouraged to cooperate with the shipping lines. As also the motivation of this work, we assume a strong cooperation between the parties involved in the maritime transportation, using some technical optimization to reduce the port congestion and improve the scheduling efficiency. Here is a simple example for the berth allocation problem in a single port. We can see that the berth is occupied by several vessels, and the later coming ones need to wait. So here is a question like, why not arrive later? The later coming vessels can slow down their speed in previous sailing segments, or postpone the previous schedules or postpone the arrival time at this port to further reduce the congestion of the port. Of the strategies based on the information sharing and the collaborative scheduling among multiple ports and the shipping lines. Based on these assumptions, we studied the continuous berth allocation problem across multiple ports. This diagram illustrates the process of this problem. We assume that each vessel has a visiting sequence, and each vessel must start at the first port at the beginning of the scheduling. We also have to solve the vessel speed optimization between any 2 consecutive visiting ports. The picture in the upper right corner is a representation for the berth allocation problem in each port. The horizontal axis is the spatial axis, which is bounded by the port length. The vertical axis is the temporal axis, which is bounded by the scheduled period. And each vessel is represented in a rectangle. The left and the right boundaries restrict the space occupied by the vessel in this port, and the bottom and the top boundaries are the start time and departure time of this vessel respectively. I also follow some assumptions in this work. First, we assume the handling time is fixed as a parameter. Second, we consider the hard operation start time window as well as the soft operation end time window. The delay will incur the penalties, which will further reflect in the objective. Third, we consider the discretization of the speeds. All the speeds, vessel speed optimization will select a speed in a given range. Finally, the safety margins and the draft depths are assumed to be satisfied. Based on these problem descriptions, we propose some methodology here. Here are some size and parameters and the decision variables used in the formulation. We just quickly see them, and the symbol of the proceeding means the port P prime follows immediately after port P, which will use in the following model. We formulate this problem as a mixed integer linear programming model. The objective is to minimize the cost for the whole system, which includes 3 parts: the vessel waiting cost, the penalty for delay, and the fuel consumption. And for the constraints 2 to 5 are relevant to the vessel time windows, and the constraint 6 to 8 prevent any 2 vessels have the conflicts in the same port. We also give a diagram to show the expression for these constraints. The beta and the gamma are decision variables for the temporal and the spatial relationships between any 2 vessels. We allow at most one overlap in either space or time, just like the situations shown in the picture A and picture B. Both of them are feasible. However, in picture C, if we can define any gap in both space and time, this is mean that there is an overlap between the two vessels, and all the decision variables must be 0. Constraint 9 further ensure the vessels burst inside the ports, and constraint 10 to 12 ensure the operation continuity in time, where the constraint 12 assume that the speeds between any two ports are constant. The last one, the scheduling period constraints, the end time for each vessel must be before the scheduled period. We further proposed a modified adaptive large neighborhood search algorithm. The framework is given in the left picture, which is based on the basic ARIS framework, and the main modification are shown in the red part of this picture, including stage-based initial solution generation. The removal and insertion operators are designed according to the problem characteristics. Moreover, we also introduced a neighborhood solution generation operation to explore a broader neighborhoods for the solutions. In this algorithm, we also consider a constraint relaxation mechanism. We first relax the constraint 13, which is the scheduling period constraints in the initial solution generation, and further reprocess the violations in the removal operation. We also relax the constraint 6 to 9, which is the non-overlapping constraints in the insertion operation, and finally remove the conflicts caused by the relaxation in the newly introduced neighborhood solution generation operation. And finally, we can get a new feasible solution. That's all of the framework of the LNS algorithm. I will further introduce some key procedures in this algorithm. The first one is the initial solution generation. We divide all process into several stages according to the cardinality of the ports, and each stage will repeat the same steps. We give a picture as example. In the picture A and picture B, the stage 1 for a port assignment. We first sorting all the vessels in ascending order regarding the handling time from the leftmost of the port to the right. As shown in the picture A. Once a vessel exceeds the port length, we mark and remove it temporarily, and we further push out the unmarked vessel to the rightmost positions in this port, like picture B, and reallocate the marked vessel to the leftmost position in this port, as well as postponing the start time of the vessel to avoid any conflicts with other vessels. This is the steps for stage. Repeat these steps in each stage, we can get an initial solution. In case we relax the scheduling period constraint in the initial solution generation, we need to remove the violated vessels in the removal operation first, and the others are removed according to the selected operators as follows, including the random remove, bit-based remove, cell-based remove, and delay-based remove. The second and third one are following the criteria about the waiting cost and average speed. And for the delay-based removal, we introduced a delay scoring mechanism to evaluate the influence of the delay. This is because the earlier delay will propagate to all the subsequent visiting ports. The equation is the calculation for the score, in which the Ksei is the delay cost of vessel I in order J visiting ports. The order J is also in the denominator of this term, which means the later delay with smaller influence. After the removal operation, we'll get an incomplete solution. We repair it in the insertion operation. We propose the 3 operators to decide the initial speed for the vessels to insert, including the random speed, higher speed, and lower speed insertion operators. And after deciding the initial speed of each vessel, we can calculate the arrival time of the vessel at current port. And we apply the similar grid insertion heuristic to get the assignment for the vessel. After that, we recalculate the actual speed for the vessel according to the results of the assignment. I will show the grid insertion heuristic using this example below. we try to insert the vessel weight, which is marked in yellow, into the current plan in this part. We first calculate the arrival time of vessel weight based on the selected operator, and considering the expected start time of vessel weight, we can define the earliest start time of vessel weight, which is the value of the red line main. And this value plus the handling time, we can get the value of the max. These two red line bounded the insertion period for this vessel, and we marked the vessel operating within this period in blue, and further eliminate the spaces occupied by these marked vessels to get the green areas, which are the available areas for insertion, like picture A. In picture B, we shift this period into, we can find a feasible position for the vessel 2 inserts, like picture C. We try to insert all the vessels into a feasible position. However, when no strict feasible region can be found, the vessel will be put on the position that doesn't exceed the scheduled period and has the minimal conflict with other vessels. This is because we relax the non-overlapping constraints in the insertion, just as I have talked before. And the conflicts will be further eliminated in the next process. This process is inspired by a puzzle game called Soko Ben. In this game, you can push a box in 4 directions, up, down, left, and right. Considering the 4 movements, we combine any 2 of them to generate 8 operators, and each one is associated with 2 directions in a fixed sequence. For example, the first operator in picture A is the right and up operator. We first push the vessel 1 to the right to eliminate the overlap. If it's feasible, we end the operator. However, the vessel 1 exceeds the port length, so we then push it up to find a feasible position. This is the meaning of the sequence of the 2 movements in each operator. We need to eliminate all the overlaps caused by the relaxation in insertion operation, and then we can get a feasible solution. Okay, that's all of the key procedures in the proposed algorithm. We further show some numerical experiments results. To test the proposed model and the algorithm, we propose 2 heuristically generated instance sets, include the Rushu instance, in which the vessel may visit a random number of ports, as well as the extreme instance, in which the vessel must visit all ports in a random sequence. The reason we highlight the extreme instance is because we define the scale of this problem by the total number of port visits, rather than just the number of the vessels and ports. And because of the time limit, I just show some results for the extreme instances. And we compared the proposed LNIs with the CPLEX. This table gives the results for the instance with 3 ports. The first column is the name of the instance, and the following are the results for the CPLEX and LRIs. From this table, we can find that the CPLEX can solve the instance, a small scale instance with 10 vessels, which is the 3rd index in the instance name, within 1 second optimally. Compared with it, the LS also can get the same optimal solution within a reasonable solving time, which is less than 5 seconds. With the increase of the vessel number, CPLEX cannot find the optimal solution within 1 hour, and there is a significant gap between the return solution and the dual bound. By contrast, the ALS outperforms CPLEX with the larger scale instances regarding a faster return time and the better solution quality, which are shown in the last 3 columns in this table. We run ALS 30 times for each instance, and the average solution and the solving time are the average value for the 30 results. And then here is the results for the instance with 4 parts. These instances cover a broader range of the vessels number. For the small and medium scale instances with 10 to 70, vessels, we can get the same conclusion as the instance with three parts. For the large-scale instances with 80 and 90 vessels, the CPLS cannot find any feasible solution within 1 hour. By contrast, the AIS also can get the feasible solution within a reasonable solving time from 5 minutes to 7 minutes. Okay, that's all of the main contents of this paper, and we will give some discussion. For the limitations of this paper, we just consider a deterministic scenario, including the handling times and the sailing conditions. We also assume a strong cooperation among parties involved in the maritime transportation, which may be challenging in practice. And we also consider a constant sailing speed, ignoring the real-time dynamic adjustments of the speed. And for the future work, the future work can incorporate uncertainty for this problem by applying a stochastic or dynamic programming. And it's also worth to explore the enhanced heuristic with the advanced strategies. And finally, from the perspective of the problem characteristics, this problem can be extended to a more practical scenarios for port operations by incorporating the joint shadowing of the key crane, the yard equipment, or the internal trucks. To the best of our knowledge, there are many studies have introduced the joint scheduling into the single port scenario. So it's also can be extended in the multi-port scenarios. Okay, that's all of the presentation. Thank you for listening.
Great. Thank you so much, Yalong. We don't have
Thank you.
in the chat box. Interesting research. Maybe I can ask you a practical question, which actually is the case for the Australian ports, not really Port of Hong Kong. Port of Hong Kong is a transshipment hub port. So too many vessels, too many coordinations. But for example, Australian ports, we have a very fixed kind of pattern of routes that basically they're kind of known. And in terms of also cooperation between ports, as far as I know in Australia, because maybe, as I said, the Australian ports are very unique in terms of, not having a high traffic of vessels. But as far as I know, shipping lines and also port authorities, they already have this information from the vessels. So basically the cooperation between ports is kind of done by the vessel operators, that they inform the next port of call that, okay, we have departed from this port, or we have this kind of plan visiting multiple ports. And then based on that, they themselves actually do the optimization. But yeah, my understanding from your model was that you developed this model from the viewpoint of an alliance of ports. Is that right?
Sorry, you mean?
So yeah, but maybe let me just simplify my question. I asked a very lengthy question. So my question is, who would be the end user of the model, do you think? Would it be an alliance of multiple ports, for example, 3 ports? Would it be one port authority, or would it be the vessel operator?
Okay. Actually, we assume a strong assumption in this work that there is a strong cooperation between the parties. So just as our objective of the model is from the perspective of the whole system. So if in the future there is a true cooperation between many parties in the maritime transportation, I think this model or the algorithm can be used in the optimization for this system. But in reality, I know it's challenging to create such a cooperation. So I'm not sure who can use it now. Yes, thank you for your question.
Yeah, my point was that the basically the vessel operator, which are mainly like shipping lines, for instance, Costco, A&O, Maersk. These guys actually are basically running the whole business and all of these optimization across multiple ports, etc., etc. So yeah, maybe just think about your end user for your research, that who would be interested in buying your model?
Actually, it's just abstraction, I
Yes,
think, for
yeah, understand.
it's an extension for the Berth allocation problem. I suppose it is a basic problem for the scheduling for the port operation.
Yes,
And
yes.
the motivation for this paper is just extend the scenario for the Berth allocation problem. And I know that the research need to get the operation in real world. So it's all just I show that we just compare the results for the numerical experiments in the heuristically generated instance. Maybe in the
Yes.
future, there is more real data we can get, and we can to explore more enhanced model or the heuristic to get
Yes.
the reality based on the real world data. Yeah.
Great, great. Awesome. Thank you so much, Yalong. I'm cautious of
Okay,
time.
thank you.
Great,
Okay,
awesome.
thank you.
Thank you. So the next presenter is Maryam, our tech staff. Listen, Maryam, please share your screen. I mute myself.
Hello.
Yes, keep going.
Great, thank you.
And share your screen.
Yes.
So Maryam is now sharing her screen. It's loading. Maryam, you're sharing, you should share the second screen. I can help you.
Yeah.
Maryam, you should unmute yourself. Yes. Sorry, guys, we're just trying to switch the screens.
Is it okay now?
Okay, let's see. Okay. And then share screen. Let's go with this. Share.
Then maybe putting it here in this. Yes. Yes. Thank you.
Can you start?
Yeah, can you hear me?
Yes, try.
Okay. Hello, everyone. My name is Maryam, and I'm a second-year PhD student at UNSW. And today I'm going to share my research on container relocation optimization and sharing the progress of my research so far. This is the outline of my talk today, and I want to start with what is the container relocation problem and why it is important. So, in container terminals, during the day, thousands of containers are unloaded from the vessels into the container terminals, and they are being stored temporarily in the area called yard to maximize the use of the space. They are temporarily stored in the container terminal in the yard in order to being ready for the pickup. Sorry, I have to duplicate slide. Okay. Yeah, thank you. In order to maximize the use of this limited storage area, port terminals actually stack containers vertically on top of each other. But the problem with this vertical stacking of container is that the high stacking density would lead to a technical problem. And that's when a container that is like a target container that its truck is waiting for it to be picked up is buried on the others. And the yard crane has to remove away all the blockers first. And these are called relocation moves, and they are unproductive and undesirable because they consume crane time and they have financial burden for the ports. So container relocation problem basically tries to answer this simple question: how can we retrieve all containers while minimizing the number of relocation and basically focus on the crane efficiency? And traditionally, this problem is approached as a single objective problem, and it's proven to be NP-hard problem. But if you look at the container movement operations, we can understand that container retrieval and truck arrivals are interconnected. So focusing on one of them solely would lead to suboptimal decisions. So on one hand, we have port operators who want to maximize the crane efficiency. So they might wait until something called natural exposure of the container, and that would mean longer delays for some trucks. And on the other hand, are truck companies whose truck cannot wait for a long time. But if we only focus on service level for the trucks, then the yard has to might to do so many relocations. So these are basically two conflicting objects, and that's why in my research I focus on joint optimization and try to minimize crane movement, or let's say minimizing the relocation, while also trying to minimize the deviation from the schedule for the trucks at the same time. In this slide, you can see the summary of the most relevant works. So some of the research focus on single objective, and those who focus on bi-objective CRP or container relocation problem only consider exact optimization or heuristic and search-based algorithm. But the problem with these are that exact optimization are not scalable, and heuristics are based on handcraft rules, and they are not adaptive. So they have to solve each problem instance from the scratch. And obviously, that's not applicable in a highly dynamic environment of container terminals. And that's why there has been a growing shift toward learning-based approaches and basically reinforcement learning. But as far as we're concerned, there hasn't been any work considering bi-objective CRP and applying multi-objective reinforcement learning on that. So that leads us to a clear gap, and that's the framework that actually my research would address. But why choosing reinforcement learning? So reinforcement learning is a very good fit for sequential decision-making problems, and CRP is inherently a sequential decision problem. So every action and decision that we made now would actually affect the future actions. And what I'm doing is that I'm training an agent that plays different scenarios in a virtual environment. It gets rewarded each time a container leaves on time, and it penalizes each time that there is an unproductive move. And over the time, it learns how these decisions can be made smarter, and also think about the next stage of the decision. In order to apply reinforcement learning, we have to first formulate a problem as Markov decision problem. So we first start by defining the state. State is what the agent actually look at. So we have the yard matrix. So this basically tells us which container is where at a specific time. And then we have different features like the current slots and the crane time remaining, the pending targets, and the blocker depths. I would also talk about the priority label in the next slide, which also tells us about the schedule of the containers and the trucks. The action here is twofold, whether it's retrieval or relocation. And if it's relocation, the agent has to also decide where to put the blocker. So the destination stack is also another decision factor here. Transition here are deterministic. So after each action, the state would be updated. And for the reward, it's like on the positive side, we have on-time retrieval and useful relocation. And on the negative side, we have unnecessary relocation. So a penalty for every unproductive relocation, and also we penalize the delays, and it would be growing based on the minutes of the delay. In order to factor in the truck appointment schedules, I've used two priority labels. The first one is dynamic priority labels, so 0 for overdue containers from the previous day. 1 is for the targets that are planned to leave today, and 2+ is for future stocks. We also have a dynamic priority label, and that would be changed based on the remaining time to retrieval. So that would be a like a general vocabulary for the agent to use based on different yard configuration, and can also give the agent the information needed to when to retrieve a container. The standard Q-learning use like a limited time horizon, but here I'm using a rolling horizon training. And the reason I'm doing this is that I want the agent to not only think about today decisions, but also about the next day. So all the base features and state would be carried over to the next day, and that would let the agent to have the freedom to learn the policy that when the crane is idle, actually doing some pre-marshalling and prepare the yard for the next stage. The pure standard Q-learning would take too long to converge. So that's why I've injected 2 domain knowledge heuristics. The first one is Q-value initialization. So the Q-value initialization is like basically for the agent not to start from the 0 Q-values and having a better guess. So it starts from the like the heuristic gives a better guess for the key values to the agent. And the next one is the rule constraint actions. So these are the actions that are like based on the port's expert opinions are like the worst decisions, and the agent should avoid it. So we omit this. These are hard coded to the agent that it should avoid making these decisions, and that would help the agent to have the like shrinken action space and actually help it to converge faster. In order to train this agent, we use the real data from container terminals in Sydney. So from all the container move logs, we extracted the yard matrix. So the yard matrix is actually telling the agent where each container is at a specific time, and also we assign a priority label based on the truck appointment system and the schedule for that containers. We fix this, we actually freeze this for a specific time and then give it to the agent as input. So 5-yard snapshots here from different months, and in total 75 bays are given to the agent to be trained on. And after that, we evaluate the agent performance on one snapshot that is unseen, which consists of 15 bays and 117 target containers. Also, all the parameters regarding the crane movement, the time for the retrieval and relocations are extracted from the real data from the container terminals. After the agent is being trained and learn a good policy, we evaluated its performance on an unseen snapshots. And as you can see here, 100% coverage rate means that all the 171 target containers are retrieved. And we have 0.5 relocation to retrieval ratio. So basically, for each 2 retrieval, there is only 1 relocation, and 63% of all these target containers being retrieved on time, and the average delay would be 53 minutes. If you look at per bay analysis, you can see that some tiers have like more shallow target containers like tier E. So 87% of these containers being retrieved on time, but there are some tiers like tier M which have like deeply buried target containers, and only the agent could only retrieve 41% of them approximately on time. And what that means for us, it means that the multi-bay coordination is like very complex compared to what we see in literature, the single bay. And that's why I've also tried to consider multi-bay, because first of all, it's closer to reality, and also having one crane share, one source being shared between different bays, make the problem make the answers more optimal, not sub-optimals. If we look at this bar chart, the crane movement distribution, we can see that the agent actually is learn a good policy. So 62% of all the relocation happen in the first 2 time slots. So it tells us that the agents learn that to relocate the blockers early when it has the idle time in the night shifts, and then focus on retrieval as the day progress. So clean early and retrieve all the day is a policy that the agent actually learn, and that's what we expected. So what this result actually tells us, so 100% coverage rate and 0.5 relocation to retrieval ratio tells us that the agent is trained and the heuristics are doing their works. But we have 63% on-time retrieval. So one point of this is related to the one crane being shared between multiple bays, And the other is that also we are trying to have very specific feature being extracted from the yard to show the agent to make more generalized decisions and like apply it into different yard configuration. But because of the limitation of tabular Q learning, the Q hit rate would be like not very much. Here is like 51%. Other times it fall into the heuristic. So that's why in the future steps and looking forward, I'm going to look at and replace the tabular Q learning with the deep reinforcement learning. So for the larger state space, that would be perfect and also can make general decisions. Thank you everyone for listening, and I'm happy to answer any question.
Right, great. Thank you so much, Maryam. All right. I don't really see any question. Is there any question or any thoughts? Please just share in the chat box with Maryam. Otherwise, we can go to the next presenter, Chuan-Lin.
Is that okay? Hello, everyone.
Chuan-Lin, we have your slides. You can start.
Okay.
If you start yourself, introducing yourself, we would appreciate. Thank you.
Okay. Hello, everyone. I'm Zi-Hao from the School of Transportation Engineering at Beijing University of Civil Engineering and Architecture. Today, my presentation is titled Robust Optimization for Joint Delivery under Order Weight Uncertainty and Wind Effects. This study focused on the certain factors in low-altitude logistic delivery, established a robust optimization model, and aims to improve the reliability of joint delivery systems in complex environments. Okay, with the development of smart logics and low-altitude economy, joint delivery has gradually become an important direction for future logics due to its advantages such as rapid response, low load dependence, and strong last mile coverage capacities. However, in actual operations, joint delivery still face three optional challenges. The first is the payload limitation. Actual order weights often divide from predicted values, and the payload variance not only affects the feasibility of joint load capacity, but also change energy consumption levels during flight. Second, there is the battery limitation. Limited battery capacity introduce the risk of energy insufficiency during mission. And the last is there is environmental uncertainty. In particular, changes in windy conditions affect the energy consumption during outbound and return flights, and further impact the payload capacity. And how to ensure reliable joint delivery descends under a certain period and windy conditions. In this system, there are a depot and some drones. Drones depart from the distribution center, return to the depot after serving customers, and then proceed to the next mission action and battery replacement. Therefore, the objective of the paper is to design a reliable drone delivery scheduling strategy under uncertainty minimizing system operating costs while ensure robust feasibility of the solution. We want to develop a reliable drone delivery scheduling strategy that minimizes operational costs while maintaining feasibility under a certain period and windy conditions. And I will now introduce the origin robust optimization model established in this paper. Due to the presence of the order weight flexion and windy conditions variance in drone delivery, if we directly adopted a deterministic model that only considering predicted weights and average environmental conditions, two problems will arise in actual operations. Increased order weight may cause the drone to exceed its maximum payload. Actual energy consumption exceeds the predicted value, resulting in insufficient battery power during flight. Therefore, this paper opposes robust optimization to explicitly incorporate uncertain factors into the model. The overall model adopts the classical two-level min-max of robust optimization structure. This formula consists of two optimization levels. The out layer, the decision maker performs the system planning, decide which drones to active, which drone serves each customer, which battery cycle to use, and how many battery swaps are needed. In short, the out level answers how should the system plan delivery schemes in advance, considering future uncertainties. And the inner layer finds the worst case scenario among all possible uncertainty realizations. And here we define the total cost consists of three parts. The first one is drone activation cost, where Y indicates whether drone K is active. The second is the battery swap cost, where the RK denotes the number of battery swaps for drone K. Continuous delivery progress follows returning for battery replacement. The second is energy cost, reflecting that energy consumption is not fixed. And the green is uncertainty set. There is a BS budget uncertainty set with three restrictions. And the main contracts protect that every customer can be served. And the next is dual reformulation of the robust model. Why we need a dual reformulation? The origin model min-max has an inner max that is an uncertain optimization problem. Commercial source like Ruby can direct handle the structure. Therefore, we convert the max into a min to obtain a dramatic MILP model. And the steps is one, origin robust model to extract inner max and maximization, apply strong duality, obtain equivalent MILP. And the first is the single or certain parameter constraint. Is payload constrictions. And is dual, and the next we get the robust counterpart, and also the single source energy constricted. We next need get the robust counterpart. And the uncertain term in the objective function is the is this purple constraints, and this is a linear maximum problem by strong duality. We convert it to the dual minimization problem. Introduce there two dual variables to improve this maximization problem. And the objective now becomes deterministic, no longer contains max, and can be directly solved by Groovy. And finally, the complete energy contraction, we get like this origin uncertain term, and to this dual problem, and we can this problem can be directly solved by Groovy. I will now present the experimental results. First, the experimental environment and the parameter setting, then cost variations under different robot bodies and out of sample relative performance. The experiments verify two questions. Can robust optimization improve reality under uncertainty? Is the additional cost acceptable? And we set the robust body setting was five numbers. As the gamma increased, the model considering more distributions, improving reality but increasing object cost due to more energy and battery swap resource. And at the picture 1 shows cost computation with the total cost increase with the gamma mainly driven by increased battery swap cost, while activation and worst case energy cost change little. This indicates the system mainly responds to the uncertainty by adding battery resource. And the figure 2 compares the relation raised under out of a sample disturbance for gamma to 0. The system fails rapidly even under small disturbance. As the gamma increase, the variation curve shifts right. The system can withstand a larger disturbance. After the gamma to 0.5, reality improves significantly, but further increase give distribution marginal returns. And summary of this results, the total cost increase molecularly with gamma cost growth comes mainly from battery swaps, not drawn current. Robust optimization significantly improves out of sample reliability, but the improvement tables offer after gamma to 0.5. And we, after determining a reasonable robustness body, this section further analyze the impact of two main uncertain factors: order weight uncertainty and wind condition varies on system goals. And first, the payload uncertainty sensitive. Fixed gamma to 0.5, vary payload relation ratio 0.1 to 0.25, and show the figure 3. Average total cost rise from 711 to 713. Cost increase mainly comes from the addition battery swap demand, because heavier orders lead to higher flight energy, lower remaining capacity, and more frequent swaps. The tolerable actual payload evaluation range comes from the 30 to 28, showing the robust model involves adequate to payload disturbance. And the next is the windy environment sensitive analysis. We set 3 windy environments are low, medium, and high, and show in the figure 4. As windy conditions worsen from L to H, average total cost increase. Battery swap cost rise from 228 to 414. The main contributor deteriorated when the increase outbound loaded energy, return flight energy, and battery cycle stress, thus requiring more swap support. And we get the conclusions. Payload uncertainty mainly affects the operations through battery capacity constraints. Windy conditions have a more pronounced impact and are the primary driver of the cost growth. Therefore, the key resource for drone delivery under uncertainty is not simple adding more drones, but enhancing battery replacement and energy support capacities. And we future work is considering dynamic windy fields, territory drones, or dynamic charging and swapping facilities. Oh, thank you. Thank you for your attention.
Great, thank you so much. Well, Chuan-Lin, right? Or your name changed to Zi-Hao. Zi-Hao, is that you or?
Yeah,
Can you hear me? Yes.
I'm a student.
Oh, okay, great. Yes, awesome. Well, great presentation. Thank you so much. And I reckon that you are basically publishing your paper or submitting your paper to a journal. The reviewers might ask about some ablation studies and if you have done any ablation study or not, because you didn't present on that. Could you? Yes.
Actually, we this paper I revised for a few times, and this is not truly the first I sat in this BTR meeting.
Okay, great, awesome. So yeah, that's the preliminary finding. Okay, great progress. Is there any question from the audience? Right, because I'm cautious of time. The next presenters are not in the room, so I have to share the screen. So they have posted their recording, and let me just share my screen. Please just post your questions or your thoughts, or if there's any relevant study with Chungjin and also the other presenters. All right, so share sound. Right. So the next presenter is Nikeshala. Nikeshala couldn't join the meeting, but she has uploaded the recording, and I'm replaying the video.
I'm Nikeshala Gunaratne from the Department of Transport Management and Logistics Engineering, University of Moratuwa, Sri Lanka. So today I'm going to present our research titled A System Dynamic Framework for ITT Automation in Multi-Terminal Port Systems, a diffusion-based approach. The supervisor for this research is Professor Niles Perera from the University of Moratuwa, Sri Lanka, and Mr. Buddhi Weerasinghe is the external advisor for this research. Okay, so first let's get an idea about the container terminal operation. So as you can see in this figure, the container terminal operation can be divided into two sections, land-side operations and quayside operations. Quayside operation involve vessel-related activities such as loading containers onto the vessel and discharging containers from the vessels. And land-side operations can be further divided into two categories, yard operations and gate operations. Yard operation is about stacking and picking containers for export, delivery and transshipment purposes. And on the other hand, gate operations handle the in and out of containers. They can be local exports, imports or ITT. So in this research, we mainly focus on the ITT. ITT means the interterminal transportation. What is this interterminal transport operations? So if we consider a multi-terminal container port, let's say with 4 container terminals, as you can see in this figure, the ITT means the transport containers between these terminals. So having an efficient ITT system is a crucial factor in a transshipment port. The transshipment is the process of unloading cargo from one vessel and reloading that cargo onto another vessel at the intermediate port. So this transshipment always requires transferring containers between terminals so that ITT operations directly affect the overall efficiency of the transshipment ports. Now let's move into the literature summary. So in this figure, you can see the distribution of studies within container terminal planning functions. So as you can see, the studies have paid more attention to quayside operation. 53% of the studies represent quayside operations, and landside operation represent around 47% of the studies. And when it's come to the ITT, it only represents 2% of the studies. In here, we can see that ITT has received very limited attention within the literature. When it's come to the port automation, in this figure, you can see the cumulative number of automated terminals and automated surfaces has increased over the time. And as of 2025, there are 77 container terminals worldwide, either fully or partially automated. And when it's come to the studies about automation in yard operations and hinterland operation, these studies have always well explored about these automations. But automation in interterminal transportation studies are always underexplored. They are limited to proofs of concepts or developing frameworks. Based on the literature review, we could identify two main research gaps and objectives. The first research gap is the lack of system-level representation of ITT automation. Existing research has mainly focused on automation at individual terminals or on specific technological and operational aspects. Although interterminal trucking is recognized as an important part of port operations, there is still limited understanding of ITT automation from a multi-terminal system perspective. Especially the key variables influencing automation and the causal relationship among them have not been systematically represented. Therefore, there is a need to identify these variables and understand how they collectively influence ITT automation. So based on this first research gap, I developed my first research objective to identify the key variables and causal relationships governing ITT automation within a multi-terminal port system. The second gap relates to the limited understanding of feedback dynamics in additive automation adoption. Previous studies have examined different operational and technological factors. However, these factors do not operate independently. For an example, let's say that higher automation adoption can influence perceived benefit and investment decisions, while investment can further accelerate automation adoption. So these interactions can create feedback mechanisms, but they have not been sufficiently explored in the context of IDT automation. So that the second objective is to analyze the feedback structure of the system and understand how behavioral and economic factors interact to influence IDT automation dynamics. Okay, now let's move into the methodology. So in this figure, you can see the research methodology that we have adopted. So we basically developed a system dynamics model. To develop our system dynamic model, we use literature analysis and expert insight. So first, we developed a set of model assumptions, and then we identified 3 mechanisms to develop the model framework: innovation mechanism, imitation, and economic investment mechanisms. Then we developed a causal loop diagram by identifying key variables under each 3 mechanisms. Then we converted this causal loop diagram into a stock and flow diagram. Okay, so this is the theoretical foundation of our study. The overall theoretical foundation of this study is diffusion of innovation theory. It explains how a new technology or innovation spreads through a society over the time. So in our context, the innovation is automated interterminal trucking, ITT. So we are interested in understanding how automation moves from being adopted by a small number of container ports to becoming more widely adopted across the industry. Within this framework, we use the Bass diffusion model to explain the actual adoption process. The Bass model mainly considers 2 forces that influence adoption. The first is innovation. It represents adoption due to external influences. For an example, let's say a port may decide to automate because of technological developments or government policies or pressure to improve operational efficiency. And the second one is the imitation. This means that ports can be influenced by what other ports are doing. For an example, if a port observes another port successfully implementing automated ITT and achieving benefits, it may become more willing to adopt the technology itself. So in simply, this innovation is adoption due to the external influences, and this innovation means the adoption due to the internal influences by observing others. In this figure also you can see this how this adoption occurs. We have 2 main stocks, potential adopters and adopters. The potential adopters will become finally adopters, and these stocks are linked through the adoption rate. This adoption rate is driven by the innovation and imitation effects. However, this Bass diffusion theory alone is not sufficient for our study, because port automation is also an economic decision. Ports need to consider the investment required and whether the expected benefits or returns justify the investment. Therefore, we incorporated an economic perspective into the model. The basic idea is that when automation becomes more economically attractive, the willingness of ports to adopt increases. If the expected return is low compared with the investment required, adoption is likely to be delayed. Finally, we use system dynamics as the modeling methodology. Basically, system dynamics allows us to bring all these mechanisms together and examine how they interact over time. This is the conceptual model framework that we have developed. So basically, we have ports with manual ITT systems, which will become finally ports with automated ITT systems. These 2 are linked through this ITT automation adoption rate. So this ITT automation adoption rate is driven by these 3 mechanisms: innovation, imitation, and economic investment mechanisms. These innovation and imitation mechanisms are captured through the Bass diffusion model. This is the data collection part. So basically, we use secondary data sources such as peer-reviewed academic literature, industry reports, and publicly available poll data to develop the causal loop diagram to identify key variables and development of the causal loop diagram. As well as we use the expert insights. We interviewed several experts from the Port of Colombo to get an idea to development of this causal loop diagram and validate the model we developed. This table shows the variables that we have identified under each mechanisms. So these are the variables that we have identified for innovation and imitation mechanisms. These are the variables that we have identified under economic investment mechanisms to be included in the causal loop diagram. After identifying the key variables, we will develop the causal loop diagram. So in this figure, you can see the causal loop diagram that we have developed. So basically, causal loop diagram captures how variables are interact with one another. So this causal loop diagram shows how IDT automation can spread across a multi-terminal port system, and also what factors can slow that process down. So in here, we have two main states. Ports that are still using manual IDT systems and ports that have adopted automated IDT systems. The movement from manual to automated is represented by this adoption rate. And this adoption is influenced by three mechanisms: innovation, imitation, and economic investment. So overall, we have 6 feedback loops here. 2 are reinforcing loops which push the adoption forward, while the other 4 are balancing loops which act as constraints. So if we take the first loop, you can see the B1 loop, it is a balancing loop. So when there are still a large number of ports using manual IDT system, there is a larger potential for innovation-driven adoption. But as more ports adopt IDT automation, the number of manual ports decreases. So the opportunity for further innovation-driven adoption also becomes smaller. So that's why this loop is a balancing loop. So as adoption increases, the remaining potential for this type of adoption decreases. Then we have this R2 loop, which is a reinforcing loop. This is where imitation comes into play. So as more ports adopt IDT automation, automation becomes more visible across the port system, and other ports can observe these implementations and the benefits they provide. And they become more likely to follow the same path. So that increases the adoption rate, which creates even more automated ports. And this further encourages other ports to adopt. So it creates a positive feedback effect. The more ports that adopt, the more likely to adopt automation. So this is one of the main mechanisms driving this diffusion of IDT automation. And if we take this R4 loop, so it is also a reinforcing loop. It is where it's introduced the economic side of the model. When ports adopt automation, they can achieve operational benefits such as improved efficiency and potential low operating cost. So these benefits can improve the return on investment. A better return makes automation more attractive to investors, which can increase investment inflow. So, and when more investment becomes available, more ports can implement automation. So again, we have a reinforcing effect. And if we take this B6 loop, it is a balancing loop, as you can see. It represents the investment capacity constraint. So automation requires financial resources. So as more ports adopt automation, more of the available investment capacity is used. So as the remaining investment capacity decreases, fewer additional automation projects can be supported, which slows down this adoption rate. So this is essentially a resource constraint. Adoption requires investment, but investment capacity is not unlimited. So we can identify that this ITT automation is not a linear process. There are forces pushing this adoption forward and also forces that slows it down. So here you can see the stock and flow diagram we developed. So basically the stock and flow diagram convert these relationships into a simulatable structure. We can see there are two main stocks, port with manual ITT system and port with automated ITT systems, which are linked through this adoption rate flow. And other than that, we have other three stocks, cumulative automation benefits, cumulative automation investment, and available investment. So in here, we have identified the mathematical relationship between these variables, basically. To conclude, so this study developed a system dynamics framework to understand the adoption of ITT automation, and this is grounded in the diffusion of innovation theory. And this model identifies three key mechanisms driving adoption: innovation, imitation, and economic investment. Especially the imitation through interactions between ports can reinforce adoption and accelerate this diffusion. And however, adoption is not driven by behavioral pressure alone. Economic feasibility plays a critical role in determining how quickly this adoption, automation adoption can actually be implemented. So overall, this study provides a conceptual foundation for future simulation-based analysis of different ITT automation strategies and investment scenarios. Moving to the limitations and future directions, there are two main limitations. First, the validation of the model was mainly based on expert insight from the Port of Colombo. So validating it with experts from other multi-terminal ports would help to improve the reliability and generalizability of these findings. And the second one is, this is a global level diffusion model. So it focuses on how ports influence each other across the wider system, rather than representing the situation at any single port in detail. So as a future detection, the same model structure could be regionally calibrated. For an example, for Europe, Southeast Asia, or Middle East, we can use this model by adjusting parameters to reflect the specific characteristics of these regions. These are some of the references that we have used for this study.
All right. So I noticed that actually we have Nikeshala with us. Nikeshala, very great presentation. I'm actually glad that we have the recording because we are running out of time, and I also have to replay another presentation. I have a few questions that actually I will post it in the chat box, and I encourage everyone to do the same.
Okay.
So let me just share the next presentation. It's loading. Just bear with me. Okay, so right, the video is here. Just a sec. Oh, sorry. I think I didn't tick the sound sharing one. Let me just redo it again. Yeah, it was already ticked. All right.
Hello, everyone, and thank you for having me at the BTR 2026 conference. I'm Nimasha Perera from the University of Moratuwa, Sri Lanka. Today, I'll be presenting my research on exploring strategic opportunities of quick and flexible expansion alternatives for transshipment hubs using Port of Colombo as a case study. This work has been carried out under the supervision of Professor Niles Perera from the University of Moratuwa and Mr. Buddhi Weerasinghe from Erasmus University in the Netherlands. To begin with, global seaborne trade is growing faster, and this is pushing ports around the world to expand their capacity. However, traditional port expansion projects are capital intensive and time consuming, and they often exceed their planned timelines by a significant margin. Now, this is a problem for any port, but it becomes especially critical for transshipment hub. Unlike gateway ports serving its own hinterland, a transshipment hub survives on its connectivity and reliability within the global shipping networks. So when a hub has to wait years for long-term capacity to materialize, that delay isn't just an inconvenience, it creates an immediate competitive risk because shipping lines can simply reroute cargo elsewhere. With that background in mind, let's look at where this risk is playing out practice. So Port of Colombo is our case study, and it is particularly relevant one. It's strategically located along the east-west maritime corridor, functioning as a pure transshipment hub that connects the major global shipping routes. Colombo's competitive advantage is fundamentally connectivity-driven, so its values comes from how well it links into the global network, not from the size of its own domestic market. Given that the connectivity is Colombo's core strength, you would expect its infrastructure to keep pace, but that's not quite the reality, and this is where the problem starts. Several critical infrastructure projects at Colombo have suffered multi-year delays. For example, the ECT, CWIT, JCT have all experienced delays between their planned and actual expected completion timelines. So the pattern here is clear. Delay is not the exception at Colombo. It's close to the norm. And these delays are not just administrative footnotes. They carry a real economic cost, which brings us to the next point. In the food industry, timing defines the competitiveness. Late capacity expansions, even when they are eventually completed, result in loss in cargo, reduced competitiveness, and even weaken the hub status. At the same time, existing terminals are forced to operate beyond their assigned capacity, which compels operators to modify how they run operations, increasing congestions and operational strains. To put a number on this, Sri Lanka Ports Authority has lost over $50 million annually because of this 5-year delay in operationalizing the ECT terminal alone. So delays not just cost time, they cost tens of millions of dollars a year, and they erode the very connectivity advantage that makes the Port of Colombo competitive in the first place. So now if delays were simply a local execution issue, the fix might be straightforward, build faster. But the challenge is bigger than that, because the entire global maritime landscape is shifting under these ports' feet. Even when expansion projects do stay on schedule, global maritime dynamics are advancing far faster than port infrastructure timelines can match. This creates a widening gap, both temporal and strategic, between market demand and port readiness. And importantly, this gap is largely uncontrollable and inevitable, yet it's critical to address. Here I have mentioned some of the global trends drive this. So ports aren't just racing against their own construction timelines, they are racing against a moving target. This sets up a clear strategic gap for Colombo especially. Let's look at where this leaves the Port of Colombo strategically. Colombo's stated vision is to be ranked among the top 15 busiest container ports in the world, but the reality is repeated capacity delays and rising competitive pressures from the other regional ports. Between vision and the reality sits a clear gap, and closing this gap is exactly the motivation for this research. When it comes to the research scope, existing approaches mainly focus on fixed large-scale infrastructure. What is less explored is how Colombo could use quick, flexible, and scalable alternatives to bridge the period between immediate demand and long-term infrastructure delivery. With that scope defined, let me now turn to specific research questions and objectives that guided this study. So here I have mentioned the identified research questions and objectives for the study. So when it comes to the methodology selection for expansion, is a complex decision because there is no single criterion that determines the best alternatives. Many criteria matters: cost, time, technical feasibility, many more. So we therefore compared several methodological approaches and selected the MCDM method because it allows us to compare multiple alternatives across multiple potentially conflicting criteria while incorporating both quantitative and qualitative judgment. So having chosen MCDM as the overall approach, the next step was to select the specific MCDM technique. So we have compared 4 common MCDM techniques. So based on this comparison, we adopted a hybrid approach of combining topses and buzzwords. So as the literature also supports, employing hybrid approaches provides more comprehensive analysis, capturing different aspects of the decision problem and increasing confidence in the outcome. So now let's look at how this methodology was actually structured and applied. So when it comes to the methodology design, this diagram summarizes the overall research design. So I'll walk you through each of these stages in the upcoming slides. So let's start with how data was collected. So we have used 2 complementary data streams. The first was literature and document review, and the second was semi-structured expert interviews involving professionals with experience in vessel and berth planning, terminal operations, engineering management, and strategic policy decision making. So the literature therefore provide the evidence base, while the experts help translate that evidence into decision-making assessments. So based on this evidence, 3 strategic alternatives were evaluated. So these are the identified expansion strategies. Traditional expansions, floating solutions, and inline departs. Let me define each of these more precisely. The first alternative was traditional fixed expansions representing long-term infrastructure such as new berths, terminals, reclamation, and dredging. The second was floating or modular infrastructure, which represents rapid and scalable capacity deployment. And the third was inland dry ports, which primarily enhance land-side capacity through inland storage. So having defined these 3 alternatives, the next question is, what criteria should we use to evaluate them against each other? For evaluation criteria were selected, each identified from the literature and validated through expert consultations to ensure relevance to the strategic port expansion decisions. So criteria are deployment time, cost, technical feasibility, and environmental impact. So experts graded each of these criteria on a 0 to 10 scale, and the ratings were average and then normalized to generate the final weight. So as shown on the screen, deployment time received the highest weight, and this directly reflects the Port of Colombo's delay-driven capacity problem. So with criteria and weight defined, the next step was converting expert judgments into a usable decision matrix. So that process happened in 5 stages. First, expert elicitation, then fuzzy conversion, aggregation, normalization, and then comes to the decision metrics, which fed directly into the MCDM analysis. Now let's look at what that decision metrics actually contained. This is the decision metrics. The most important point here is that the metric does not simply assume that a higher number is always better. The preference direction depends on the criterion. For example, lower deployment time and lower capital cost are preferable, whereas higher technical feasibility are treated according to their defined preference direction. So, and also the indicative ranges from the literature were also used to define and check the experts' assessments. When it comes to the data analysis part, after the decision metrics, we have conducted the topses analysis first, and then went to the first pass analysis. So after the topses, we have conducted bus method. The most important result is the consistency between 2 MCDM methods. Both of topses and bus identify floating or modular infrastructure as the highest performing alternative, followed by inland dry ports, while traditional expansions ranks lowest under the evaluated criteria. area. So this consistency is important because the result is not dependent on a single decision-making technique. Then we have done a scenario analysis to check whether these results hold under unanswered. Then next we comes to the findings. So 4 operational insights has been emerged. So first, Berth's capacity is critical bottleneck, particularly under high berth occupancy and vessel bunching. So this supports the role of floating infrastructure as a rapid seaside capacity option. Second, land side capacity is also under pressure with a high yard utilization. So this creates a role for inland transport. Third, infrastructure delivery is not keeping pace with the speed at which capacity pressure can emerge. And finally, these findings suggest that traditional expansion alone is insufficient as a short to medium-term response. So taken together, Colombo's challenge is not only insufficient capacity, but insufficient adaptability to changing maritime conditions. So now let's check how these findings align with the Colombo's own official master. When it comes to the alignment with the master plan, so 3 points of alignment stand out. The Southport Max development requires a phased implementation, so flexible solutions can provide bridging capacity during delays. Second, ECT, WCT, and SHGT expansions involve lengthy constructions where floating terminals and inland dry ports can support operations during capacity transitions. Third, with Northport development plan for future demand beyond 2040, modular solutions provide scalable, low regret capacity under uncertainty. So overall, flexible expansions complements rather than competes with the master plan, strengthening its resilience. We benchmark Colombo against regional port characteristics using CPPI trends from 2020 to 2024. For a strong alignment is seen in South Asia and Middle East, where capacity pressures, transshipment dependence, and disruptions favor flexible solutions. Alignment is more moderate or partially in East Asia, Europe, and North America, where efficiency, sustainability, and resilience are stronger priorities. Overall, the findings suggest that flexible expansion is context dependent rather than one size fits all. So when it comes to the discussion, what this research points to is a shift from a traditional paradigm to what I would call an adaptive port paradigm. The traditional approach emphasizes physical scale, large fixed terminals, long-term forecasting, permanent infrastructure, and maximum capacity. The future-oriented approach instead emphasizes strategic flexibility, modular capacity, demand responsive planning, scalable solutions. So in short, for transshipment hubs, competitive is shifting from how a large port is to how quickly a port can adapt. So this conceptual shift has direct implications for policy and investment, which brings me to the next slide. So here I have mentioned some identified policy and investment implications we identified throughout our study. Another discussion point is a new port model. So here we have mentioned adaptive sea land port model. So this model shows Port of Colombo's port system supported by 2 independent, quickly deployable buffers. On the seaside, floating and modular capacity act as a buffer against the berth scarcity, and on the land side, inline dry ports act as a buffer against yard saturation. So in the essence, this is a dual buffer capacity model. Berth side and yard side pressure are absorbed by 2 independent buffers around the same port system rather than relying on a single point of expansion. So these are the contribution of my study. To conclude, I would like to leave you with one central idea. So what I want to say is, in modern ports, strategic values lies on not only in scale, but increasingly in flexibility, the ability to adapt capacity to changing demand and uncertainty. So that's about my presentation. Thank you for listening.
All right, so with this, we can actually call the end of this session. Thank you so much for everyone attending. Nimasha isn't here in this room, so we can't really ask any question, but please stay in the room if you are interested to attend the next session of the BTR, which will be the future transport research presented by the National Transport Research Organization. Yeah, otherwise, please feel free to grab a coffee or tea and come back to this room. But also, there are other parallel sessions. You can again check the conference program on the BTR website. I can also share the link to the next sessions. Yeah, so we will reconvene actually in a few minutes. Thanks, everyone. Hi, Ronnie.
Hello, how are you?
Sound. Let's just make you co-host. We're waiting for David and the rest of the team, right?
Yes, they should be here very soon.
Maryam, can you please make Ronnie as co-host?
They said they're all waiting to be let in.
Oh, we don't really see here in the waiting room.
Interesting.
Are you sure that they're in the right room?
Let's see, all right.
I've sent a Zoom link again. We have Fazil. No, the presenters should be definitely David. Yeah, we don't actually see anyone in the waiting room.
Okay, they might be in the wrong link then, huh?
Yes, so we still have a few minutes. That's all right. I sent the Zoom link to David again. Okay, we have Safarnezhad now.
There you go.
Hi, Safarnezhad.
Hi Ellie, how are you?
Yeah, good. And also we have Robert and we have David. Now we have everyone. Are we waiting for Charles? Hi, everyone. Hi, David.
Hi, Ellie. How's it going?
Good, good. Thank you. Maryam, can you please co-host David, Safarnezhad, Robert,
Hendrik.
and Henrik? Nice meeting you, Henrik.
Yeah, likewise.
You're a new NTRO employee. I mean, not new, really.
Well, almost 4 years.
Yeah, time flies.
Yes.
I left NTRO in 2022. So I'm ex-NTRO employee.
Yep.
Right, so we have Robert. Are we waiting for Charles as well?
He's not talking, but
No,
he'll be
okay.
observing. Yeah. So we can probably get started. Yeah.
Okay, David, you are the session chair. Over to you. I mute myself. I'm in the background. Looking
No
forward to
worries.
hearing from you guys. And again, very nice actually to see your faces.
Yeah.
Good to
Thanks,
see you
Ellie.
as well.
Yes. Okay, we'll get started. Yeah, so thank you everyone for joining us, and thank you for the Bridging Transportation Research Committee for allowing us to do this presentation today. Yeah, so we're going to be talking, our session is called Recent Research at Australia's National Transport Research Organisation. Am I still sharing my screen, by the way?
Yes, David, you should.
Yeah.
You're a co-host, yes.
Is it
Just-
sharing or has it disappeared? Oh.
Can you see the share icon?
Yeah, I thought I was sharing. Sorry, let me disappear now. I'll just hold on.
It's I see that you are a co-host, so you should be able to share.
Yeah. Yeah, I thought I was. Just bear with me for a sec. Oh, okay. I can't see. Must have hidden.
Right, you can't see the share.
Yeah, I just clicked something and it disappeared on me. So just hold on. Let me work this out.
Oh, maybe it's on your second screen. That's the problem whenever you have multiple screens.
Here we go. I think I'm back in action.
Great.
Maybe. I can see something. I'm not going to. I'm not going too well here.
No, that's all right, David. Take your time. I reckon that you have multiple screens, and when you click on share screen, then a bar appears in your perhaps second screen at the top. So look at the top. Yeah, no?
Yeah.
I don't know
So
what you see, but
I could see the option to share, and I thought I was sharing, but then I clicked on something, and then the that little window has disappeared, and now I can't see. And now Kenneth's coming in to help me out. So.
yes, Kenneth, go for it. Hi, Charles. Nice to see
Click
you.
on that, baby. Yeah, here we go. Back in action. I'll share again.
Beautiful.
And then share.
Awesome. It's loading.
Now that should be working.
Yes, we can see it. Perfect.
Yes.
Over to you, David.
Yes, over to me again. Take two. Yeah, so today we're going to be talking about some recent research at Australia's National Transport Research Organisation. A little bit of background about us and about myself. So I'm David Green, Principal Engineer within the Transport Futures and Transport Futures Portfolio Lead within the Asset Performance and Safety Business Group. And today we've got 6 speakers, a bit about myself, and I'll just provide, I'm the chair and providing an introduction, just a bit of an overview of NTRO and Transport Futures. Then we've got Dr. Ronnie Kutanarata, talking about understanding the pathway for automated bus operations. Kenneth Lewis on way in motion into the next generation. Dr. Sefa Dekordi on applications of advanced analytics, AI and machine learning. Dr. Robert Cohan on EV developments in Australia and New Zealand. And then Dr. Hendrik de Linden on improved capacity guidance for motorways in Australia and New Zealand. But I'll do about 10 to 15 minutes each with a bit of a Q&A session at the end. But a little bit of a quick overview on NTRO and Transport Futures, because we may be talking to an international audience. So NTRO is a global leader in innovative transport solutions, and we provide integrated transport. We're integrated transport and innovation driven. So we drive innovation and deliver solutions, and we do that across various sectors. So we're the transport research organisation, and so we cover all transport modes, road, rail, ports, airports. Our bread and butter, or our historic focus has been on roads, but we've expanded recently into rail, ports and airports. And we look at asset performance and structures, infrastructure measurement, safer, smarter infrastructure, sustainability and materials performance, training and certification, data technology, and transport futures. And that's where we kind of sit in today. A bit about our background. So we're a not-for-profit, and our shareholders are the Australian and New Zealand transport agencies. So we don't have direct government funding. We have to stand on our own 2 feet, but they're our shareholders, and we work for them, or we provide services for those agencies, as well as private organisations and private industry. We also have affiliations with the 7 global research laboratory organisations around the world, both across US, Asia, and Europe. So a bit about Transport Futures. So we're essentially investigating methods and policies to enable the safe, efficient, productive, and sustainable movement of people and goods now and into the future, and that's across all transport modes, across road and rail, from cars and public transport to freight and personal mobility. And we've got 8 service areas, which I'll go into a little bit more detail across the next slide, so I won't list them all, go through them now, but there they are on your screen. And we've got various key experts that work across our portfolio, with myself as the portfolio lead, Dr. Charles Carl as the national technical lead, Vivica Matthews providing some strategic delivery advice, and experts in those various service areas. And we've got a few of them here today to talk on some of their recent research. And a bit about the various service areas that we deliver. So traffic and transport engineering, so advice focused on a safe and efficient movement of people and goods. Policy guidance aimed at optimising the transport networks by aligning capacity with demand and aiming to maximise network efficiency, reliability, and overall performance. Then the intelligent transport systems, so advice on planning, implementing and managing intelligent transport systems and related assets, support the enablement of connected and automated vehicle operations, and guide the deployment of ITS roadside infrastructure essential for a productive, increasingly CAV environment. Then managed motorways, and we've got one of our key experts today who will talk about this, in Dr. Hendrik de Linden. And so that's lead the development of managed motorway practices across ANZ, provide advanced freeway capacity analysis and performance methodologies, and evaluate and optimise smart motorway designs to enhance network efficiency. Then we've got connected and automated vehicles, and so we've got our expert in that, in Dr. Ronnie Kutanarata, talking today, and that's around leading CAV trials, including test beds and proof of concept deployments, develop safety cases, risk management and regulatory approvals, and design and deliver research, testing and data-driven reporting. We also work in the heavy vehicle safety and access space. So we analyse heavy vehicle safety and access using advanced modelling and performance assessment, test rollover risk, safe operating speeds and route suitability for high capacity vehicles, and apply load transfer ratios, simulation and performance-based standards methods with field testing to improve safety outcomes. We don't have a speaker today on that, but our expert in that space is Anthony Jimenchik. Then we've got low and zero emission transports, and we've got a speaker today talking about that from Dr. Robert Cohan. And so we lead research and guidance to accelerate low and zero emission transport, contribute to and assess vehicle infrastructure safety and policy, including hydrogen, EVs, fire risk, pavements, accessibility, etc. Although we don't do the pavement work directly ourselves, that's in another portfolio within NTRO, but we do provide guidance around, I guess, the potential for heavier low and zero emission vehicles and the impacts on those pavements, and to deliver evidence-based solutions to enable safe, sustainable and inclusive mobility. Then we've got data analytics and intelligence. We've got an expert today on that, Dr. Szeto. And so we lead data analytics and artificial intelligence for transport safety and automation, apply advanced sensing and machine learning, so LiDAR, cameras, inertial measurement units and computer vision, and deliver predictive models and insights to support safer data-driven decisions. And then last but not least is our rail service area. So look at ITS, level crossing technologies, accessibility, asset monitoring and intermodal terminals, and develop practices that improve performance, reduce costs and build capability. And then our work spans both rail and the interface between rail and road. That's a bit of an overview, quick one around our various service areas. And as I mentioned earlier, we got 5 speakers today talking about various research that they've done across those service areas. So our first one will be Dr. Ronnie Kutanata, understanding the pathway for automated bus operations, then followed by Kenneth Lewis, way motion into the next generation. Dr. Szeto Dakordi will talk about applications of advanced analytics, AI and machine learning. Then Dr. Robert Cohan on EV developments in Australia and New Zealand, and then Dr. Hendrik Zelinden on improved capacity guidance for motorways in Australia and New Zealand. So roughly about 10 to 15 minutes each. We'll just go through all the presentations, then we'll have a bit of a Q&A session at the end. So that's a little bit of my contact details. Now it's opportunity for Ronnie to talk. So I welcome Dr. Ronnie Kutanata, who's our senior engineer at NTRO, and he specialises in automation, optimisation and emerging technologies research, and will share his insights on understanding the pathway for automated bus operation. So over to you, Ronnie.
All right, thanks, David.
I'll stop sharing my screen.
Yep, and I'll share my screen.
And you'll share yours.
Okay, hopefully that shows up now. So yeah, thanks everyone for attending once again. What I'm going to present today is really what we think about automated bus operations in Australia and how we can achieve sort of a public, how we can use this and leverage this technology to improve transportation in Australia. Particularly, we're looking at public transport, of course. But what I'm going to talk about today is really just what we've done so far, and sort of what are we planning for the next steps. So just to provide a bit more context and a bit more rationale about why we're doing this, we consider, or I like to think about holistically. And when we consider all these different transport modes, like ranging from active transport up to heavy rail. So what we're focusing on is automations for usually road-based modes, right? So and we've dabbled in some of these modes, like starting from the low capacity shuttles, the low speed shuttle bus, and up to now we're looking at buses. Now, in addition to automations, I personally have, and we as a collective have looked at individual supporting research. Like we look at, for instance, in the digital side, we're looking at our algorithm for on-demand transportations, and also, just give me 1 second. And also looking at system optimal recommendations for transportation modes, if you would like to optimize people's movements. At the same time, we also look at from the planning side about how we can achieve 20-minute neighborhoods with a smarter facility placement around the area, and also looking at behavioral change projects, looking at more choice and how we can influence people's behavior. But the point I'm trying to make here is that we integrate all these diverse technical aspects and try to bring them all together into a cohesive system, right, for a smarter and more sustainable transport future. Now, focusing on bus, right? So the idea here is that we try to improve road-based transit service. So with bus services, the usual treatment, so to speak, is to create a dedicated infrastructure, so busways, right? But in order to deliver this, it will obviously involve quite a bit of cost because you need to build the infrastructures. You need to deal with the constructions as well, like the delivery timeframes. Any kind of like delays or disruptions may put more risk into your investments, and you need actually the space, right? So you have to acquire the lands or the property to actually build it. So the question then, how do we make the best use of existing road space? And one potential solution is to use automation, right? And in addition to obviously efficiency, we also try to see if we can then how automations can actually improve safety for bus operations. And to be honest, in fact, I think the industry, the people from the industry that we've spoken to are at the moment are more excited about the potential safety improvements from automation. So what NTRO has done in this space is that we have done quite a bit of projects starting from 2015, where we've done some trials since then, or assisting other people, other organizations to undertake their trials, and this is done mostly on public roads. And as I've said before, we've looked at light vehicles, we've looked at the low-speed shuttle bus, we've looked at heavy vehicles like trucks, and now we're looking at buses. We also try to look at this in different fields, in agriculture and also for defense application. And me personally and the NTRO as a whole, our focus is looking at the safety plan, right? So usually our role is developing the safety management plan just to make sure all these trials can run well safely. Now I do have a bit of video here. I'm pretty sure I've clicked share sound, but if the sound is not playing, do let me know, David.
Well, Rita is the first fully autonomous bus ever to hit the road in Australia. So we're very proud at NTRO to partner with Tier 4, our global partner, to put advanced autonomous systems on a bus, which you see behind us here, that enables that bus to travel and serve use cases across Australia and New Zealand, taking real people on real roads, delivering real tasks. NTRO is bringing that technology here to Australia, as I said, in partnership with Tier 4. It's a wonderful way of delivering the next step of advancement on our road system, serving use by the community. NTRO, in partnership with Tier 4, have said, now's the time. We've bought the bus, we've made it available to state, territory, local governments, private sector right across Australia and New Zealand. Now's the time to engage, to work out your use cases and how we can support you on your journey.
Right. So essentially, NTRO has purchased an automated bus. So this bus has a level 4 capability. And it's actually we form a partnership with the company who who developed this bus, which is Tier 4. Right, so this is a medium-sized bus, we call it. So it has 23 passengers technically, including standing passengers, but it's limited to about 13 passengers because of the seating requirement when we operate this in automated mode. So the bus is equipped with multiple types of sensors, LiDAR, radar, cameras, GNSS, and IMU. The software that's being used is from AutoWare, you see. So it's open source, and it can be accessed by essentially the public. And this is also why we sort of prefer a Tier 4, because of this transparency that it brings. The bus can operate up to 40 km/h in automated mode, and it's an electric bus. The body is from BYD. Just to elaborate a little bit about the automation technology. So how it operates is that we first have to create a route, like to create a digital map and create a route for the bus. And what the bus will do is that if we specify a point on that route, then the bus will navigate along the route to that point that we have specified. So if it makes a stop, let's say at a bus stop, then before it will resume the trip, it requires authorizations from the safety driver. And if there's ever need for a lane change, then it will do so automatically. It will decide to do the lane change automatically. We just need to make sure that the route contains a segment with multiple lanes where it can perform the lane change. So because we're essentially still, under the trial phase, we actually need 2 personnel to operate the bus. One, a safety driver who sits on the driver's seats, and the second is the safety operator who sits just behind the driver. Well, whenever on the bus really, but usually sitting behind the driver, because then they can see the display behind the driver's seat, as you can see in the picture there. The safety operator's role is to monitor that screen and to make sure that everything is going all right. And the safety driver role is really just to make sure and take control if anything were to happen. So once we brought the bus to Australia, which is quite a lengthy process in itself, but what we've done is to make sure that the bus is ready for future testing, right? So we have brought the bus to a test track in regional New South Wales, and we've done some evaluations. So there are essentially 3 things that we've validated. Firstly is the established test cases, which essentially different kind of scenarios that are commonly found in Japan and Australia. But we've also do some work to actually introduce, or test cases that are quite unique to Australia. So for instance, the traffic light settings are different in Japan and Australia. Sorry, did I say the bus comes from Japan? But it did come from Japan. So the traffic light setting in Japan and Australia is different. So that's why we have to do some data collections in terms of the traffic lights. But also we've tested on some unique Australian wildlife, such as kangaroo and koalas. And then we do a whole route test or demo, like what you see in the bottom image there. So the bus can actually make a loop around that without the driver having to intervene. In terms of safety assurance, there are actually multiple aspects to consider with multiple stakeholders, including the site manager, our own compliance teams and safety teams, the insurers, the test engineers, the safety engineers. Now, if you were to do it on public roads, we have to also get in touch with road agencies. And if we're operating in a precinct, then we have to go and speak with the precinct owner. And also we usually get in touch with the emergency services just to make sure that they're aware of our activities. The main point here is to make sure that we have clear responsibilities and accountabilities among the stakeholders. Then in terms of the diagram there, it just shows the multiple aspects of safety that we need to consider. including transportation of the bus, any on-site safety, general vehicle operations, safety related to electric vehicles, such as the charging requirements, and then any kind of like safety measures when we're doing any kind of testings in relations to the automated driving system, safety when handling visitors on board, getting on board the bus, and to make sure that who's responsible in making sure that this safety plan is continually being updated. I'll go through some findings here, which I've categorized into 5 blocks. From the automation perspective, we found that the technology performs very well. I mean, it's no surprise, to be honest, because this technology actually has been tested quite extensively in Japan. It has been operating on public roads. From a system perspective and in terms of usability, we found that the the interactive mapping is quite easy to use. There's clear visualizations, but we've identified that there are perhaps more sort of unique test cases that are unique to Australia that we probably need to keep working on. Now, looking at perhaps towards more into the futures, based on just our experience doing these validation tests, we think that the bus size, because this is a mid-sized bus, so this is not a large size bus, we think that the size is appropriate for a starting point to do proof of concepts around Australia, really. And to be more specific, we're thinking if we're able to deploy this perhaps in regional areas or smaller suburbs to serve the local area, this could be promising, or precincts, of course. Looking at the ecosystem-wise on how we can make sure that everything runs smoothly. As I said earlier, it requires a lot of stakeholders' involvement to make sure this can run properly. So we have to consider all those as well, such as the training data, making sure that we have enough local training data to build up those unique test cases, connectivity and charging infrastructures, and software licensing, if any, and also upskilling the local workforce to make sure that they can operate the bus properly. So if you were to be able to deploy this bus for multiple different proof of concepts, then we think that it could be useful and provide us some insights into I guess for future full-scale deployment, right? So, and we also like to use this opportunity to actually use the bus, I guess, as a test and research vehicles, and we can use this to as a knowledge transfer. Now, what are the next steps? Now, I've listed some points here that we are doing at the moment. So the first is that Tier 4 themselves has mentioned that they are updating the automation system using state-of-the-art technology. We also will investigate the industry needs and gaps that can be addressed with automations, and then we can progress to further tests and doing trials, focusing on the use case that can readily benefit from the technology as identified by the industry. We are also thinking about undertaking research on human factors and passengers' experience, particularly interacting with the automated operations such as boarding, any kind of signage accessibility, because nowadays with drivers on board, they serve as a customer service I guess personnel as well, but without, let's say in the future, without drivers on board, then how would that work? So that's my presentation. Thank you very much for listening. Handing back over to you, David.
Great. Thank you, Ronnie. I'll just reshare my screen. Yeah, so yes, thank you, Dr. Ronnie, for your presentation. Now we'll pass over to Kenneth Lewis, who works mainly around our ITS and traffic engineering service area, but also across the other areas. But today he'll be talking about way in motion into the next generation. So yeah, Kenneth Lewis is our senior engineer at NTRO, and he's worked on transport research projects across network operations, heavy vehicles, intelligent transport systems, and road safety, and will share his insights on way in motion into the next generation. So over to you, Kenneth. I'll stop sharing.
Thanks, David. Sorry, getting... Okay, so a bit of a background as to why this is important. Transport agencies have been looking after a large network of roads and bridges on which they maintain, with this network including aging infrastructure. These networks are being loaded with heavier and heavier vehicles, with industry wanting to increase their productivity. And as such, there's a need to understand what loads are actually being operated on these networks, and the impact that they're having on it. If the transport agencies know what they're actually having to deal with in terms of the loading, they can provide greater access to these vehicles. So they need to balance that productivity and the risk of damaging the infrastructure. So that's understanding these loads and where they're happening is part of where way in motion comes in. So way in motion is one of the tools which is used by the transport agencies. There's obviously other technology which can be utilized, such as onboard mass and even telematics can provide an insight into where these vehicles are operating, but they all serve different purposes. In regards with way in motion, there's different types of sensors which can be utilized, each with their benefits and disbenefits. So some of those could be the cost of the sensors, the accuracy, the sensitivity to the natural environment. Some of these sensors which are used may be piezoelectric, piezo quartz, bending plate, or capacitive sensors. So the way in motion itself detects the axles and mass which pass over the sensor, and that can be used to allow for the identification of the number of axles, the spacing, and the associated mass of the vehicles. So this in turn helps to provide the crucial information required in the planning and asset management, such as historical access, compliance, and loading of the vehicles. While way in motion provides useful insight, there are other technologies which transport agencies utilize, as mentioned, and they may be complementary to way in motion if they're utilized right. So as part of a project which was undertaken as part of the National Asset Centre of Excellence, or NACO, NTRO looked at enhancing way in motion with some of these complementary tech data sets, while looking at enhancing way in motion. So what we can see on the right-hand side is a bit of a visual representation of a concept which was developed as part of this project, which was virtual way in motion. While we considered a number of technologies and looked at the technologies, our process didn't necessarily get to look at the data sets of some of the technologies such as ANPR and onboard mass management, due to the availability of the data. So what this highlighted was that while these data sets aren't used for the same purpose, they can be used to enhance the technology which is currently utilized. So as part of the review, a proof of concept was developed, which looked at extrapolating mass from weighing motion sites to classifier sites. And this considered the similarity of the vehicles and the distribution of the vehicles based off of the axle configuration and spacing of the vehicles. As part of this process, we looked at extrapolating the mass from weighing motion sites to other weighing motion sites to get a bit of a sense of how well it was working and as a means of validating the method. So building upon this extrapolation of mass and the virtual WIM concept, another use case which was considered as part of the work was the tracking of the larger unique vehicles. And the process which we used here was a bit more of a de-identified way of tracking the vehicle as opposed to, say, something like ANPR. This looked at understanding where the vehicles may have traveled, which is important as it helps to inform a better understanding of the structures which may have been crossed by these larger oversized, overmass vehicles, as that's something which the transport operators have little oversight on at the moment. So as part of the use case, we looked at large class 1 heavy vehicles, so in particular low loaders and load platforms, as they have a relatively unique footprint which can be tracked across classifier sites. Based off of these axle spacings, routing, and the time gaps between when the vehicles were logged, this helped us to understand where the vehicles were potentially traveling and the routes which they were taking. So what we can see on the right side of the screen is a bit of a understanding of the vehicle configuration and the masses of some of the vehicles which have been logged. So where to next? An Austroids project is currently starting up, and this is looking at the practical consideration of the deployment of weighing motion, and this will be led by NTRO, who will be working alongside some national and international experts in weighing motion. This work aims to support the deployment of weighing motion and complementary data sets or complementary technologies to enable road managers to make informed decisions. This will be enabled through guidance on weighing motion and complementary technologies, the standardization of data for national consistency and comparability, the integration of technology, considering security and privacy requirements, the establishment of an evidence-based evaluation framework for weighing motion, and this will help to support investment through the development of a cost-benefit analysis methodology, improve network maintenance and upgrade planning, and help to improve the confidence in heavy vehicle compliance. So if any of you listening have anything you would like to be considered as part of this work in relation to the next generation of weighing motion, alternate or complementary technology, whether it's case study, research, or technology available in the market, please feel to reach out to myself or the team.
Yes, thank you, Kenneth. Much appreciated. And there's opportunities for questions for Kenneth and Ronnie and all the other speakers at the end of our session. So I'll just reshare my screen. Yeah, so next up we have Dr. Safarnezhad Dakoudi. So we are pleased welcome Dr. Safarnezhad Dakoudi, Principal Engineer at NTRO, who specialises in artificial intelligence, advanced analytics, and emerging transport technologies research, and will share his insights on applications of advanced analytics, AI, and machine learning. So over to you, Safarnezhad.
Yeah, thank you, David. I'm going to share my screen. Yeah, thank you, David, for the introduction, and thank you, Dr. Eli and the team for this opportunity so we can talk about what we are doing and what is our research. I'm going to talk about application of advanced analytics and machine learning, but I was thinking it's better to maybe start with the motivations and the way that we are looking on the holistic way of data integration in different area rather than coming with different use case in the very short summary. So provide an environment that we can kind of create that collaboration opportunities in the future. So as you can see, the area that I'm working is asset performance and safety. And during the period of the time I'm working at NTRO, I realized that how these two areas are harmoniously blend together. So I'm going to talk about why we need a new approach, why the data-driven approach is important, and specifically from the safety perspective. So if you look at the historic crash data within Australia, there are always a trend, the downward trend, and there was some intervention from seat belts, from speed cameras, from the new regulation, and we reach a point that we saw there is no other improvement, and also there is increase in the road crashes if you look at the trend. So it comes to the fact that we are analyzing the crash. Of course, they are very valuable data and we can understand what is the reason behind this, but my mentality is more on the proactive side, and I'm try to understand that crash is no longer be our wake-up call in road safety. And our connected world now provides foresight through digital twin and enabling actions before life are lost in our network. So that is the mentality behind the area that I'm working and motivates me to look at the problems from data-driven point of view. If we look at the gap in the safety data from infrastructure, behavior, and risk, we saw three different area of the work that people usually work around it. So we have infrastructure factors in our safety, and then we have commuter safety and the behavioral factor as well. So either they are work together or isolated when we are doing our analysis, but the core element here is when we can concurrently look at all of these three factors at the same time. And when we look at the current data that we are working with, usually, for example, with the crash data, they are often sparse and also may not accurately reflect the level of risk we have on the network. Usually, the data for network operation, they are collected in a short period of the time, like 2 weeks, 1 week, 1 month, and usually insufficient data for analysis. And then we come up with underlying various infrastructure characteristics that can impact driving behavior and route choices that we have on our network. And let alone we talk about the application of AI and lack of proper definition of AI and automation in hazard analysis on transport safety. So when we define the new automated functionality and it provides new safety risk, how we can quantify that kind of information. And at the moment, it is a kind of gap needs to be investigated. So where we can overlay these kind of data together and come up with a structure, the holistic structure of the data that can understand the problem and then we can solve the problem from that. So the flow chart you see here is actually the mindset that I have for the projects that I'm doing. So we gathered infrastructure survey data, and asset intelligence is the area of the work that can provide this information. We have system connectivity, the connected vehicle data, the ITS technology that can gather this information, and we have a rich digital map in a different layer that can be embedded to all of this data and provide the situation that we can collate this data together. And of course, other sources can come from the local governments, can come from the federals and agents, and we can add them together and create a intelligence digital model of the road network. So if this collation is properly defined, now we have an opportunity to create different agents to work on the safety, to work on the asset part, to work on the asset intelligence parts and the network operation side, and understanding more about the surrogate safety measures, understanding the pattern and also behavior insights. So what I want to mention is a vision for safer road is transmission from passive safety and have more preventive and active safety. Obviously, with the active safety, there will be some errors because we try to predict, we try to do the prediction around the observation that we have. But the benefit is providing this kind of system in the SME, subject matter expert in the loop. So we narrow down the problem for our subject matter expert rather than looking at the whole network. They can look at the specific problem and then they identify the problem and solve that problem. I'm going to talk about a couple of use cases that I was working and also some example and see what is the future look like. So the first examples that I want to highlight is something between asset intelligence and asset management and also the safety. We know, and the literature also shows that the safety, the roughness of the road has impacts on the safety. However, for gather the roughness of the road, you need to have a survey vehicle going and collect the data for you, which is the current survey that NTRO is doing with the national survey vehicles and obtain the sensor level, laser level accurate roughness measure from the road network. On another side, we talk with a connected vehicle data provider like Compass IoT, and they provide the rich data in terms of connected vehicles and in the different locations with different market penetration. And what we saw, we can overlay the 10-meter interval ground truth data from NTRO and then look at the observation of the vehicle type and also the motion of the vehicle from the connected vehicle data like Compass IoT, and then we do the ground truthing and we can develop a model, a machine learning model to understand and predict the roughness of the road with some level of accuracy. What we observe in 3 different layers, fair, good, poor, if you want to classify, we reach 76% accuracy. So definitely connected vehicle cannot replace a sensor level measurement. However, with the data, you have a digital infrastructure that you can understand in which area of your network you can focus further and then do the survey and do the priority of your work. So that's the benefit of using connected vehicle data, and you can manage your program of the work using that kind of output. Another example is about the network operation. So within the National Asset Center of Excellence, we have a project with Transport Main Road Queensland, which is about understanding the application of connected vehicles in the network operation. And one of the examples here is for travel time and having devices, the Bluetooth devices across the network. It is possible to transform and change this physical infrastructure to a digital infrastructure. And then we do whatever we are doing, for example, with Bluetooth devices, with a more different granular resolution using connected vehicle data, and the OEM level speed comes from the telematic data. So we start to do that kind of analysis, and we find, for example, you can proactively look at the queue length or excessive queue length within your network, in your corridors, and also understand some kind of proxy-based method to estimate the back of queue using connected vehicle data. So it is a proactive way because you can analyze all of your network and identify the problems and pass the problems to a subject matter expert, and then they can start do the analysis and understand and find a solution for it. The other example was in the same corridor, we had a look on the connected vehicle data and the queue length, and we saw how does it look like. And we find out that, for example, in a specific intersection, there is a drop of the speed around 50 meters after the intersections when we analyze all the data together, and we didn't know why. But when we split the bus from private cars, from other cars, we figure out that that was because of the bus categories in our data. So we look at the map and we figure out that there is a dedicated bus stop in the data that we have. So what it says is also important to distinguish between vehicle type and also trip purpose when we want to do the corridor performance analysis. Some other example of the works that we conducted related to using mostly data-driven approach and advanced analytics was looking on automation to improve Australian level crossing assessment model. So ALCAM at the moment requires a manual survey. So we look at how we can change this manual survey to a digital survey. So we have a digital twin from the infrastructure and do that survey. And we saw that it is very practical to do it. However, there is a limitation, and the limitation is you need to provide an accreditation process to understand what is a minimum requirement coming from all of these machine learning and AI algorithms to detect the parameters you have in your safety. So that's a part that we are at the moment investigating and have projects within the NTRO to investigate what is that accreditation pathway look like. The other projects, for example, it was defined back in 22 about identifying the hazardous locations within the head-on collisions for roadside objects. And actually what we call that, it's a killer tree. So the trees which is close to the road. I put it specifically this example because with the on the time back in 22 with the spatial lab funded projects from Transport Main Road Queensland, it was detecting the tree trunk with the computer vision was a project. And now we are in 2026. That kind of application in computer vision is very straightforward. And it can be easily done in terms of semi-supervised or unsupervised training to identify that kind of application. So this kind of area is evolving at the moment, and I think the pace is quite fast, as you can see in the last couple of years. And also the other application is about local government safety and the data-driven insights from collating different sort of data from different sources from local governments to identify the safety patterns within the local government, which is at the moment the projects within the Western Australia Road Research and Innovation Program. So what is the future look like for us? I would say the integrated asset intelligence, safety analytics, and road user behavior data can support the proactive safety application. We need to align and connect diverse data source and creating that kind of holistic digital view of the road network. And finally, we need to leverage integrated insight to identify emerging risk and evidence-based safety interventions. Thank you very much for your time. David, I pass it to you.
No worries. Thank you, Dr. Seppa. Much appreciated.
Thank you.
Okay, so as mentioned earlier, yeah, Seppa and the rest of the crew will be available at the end for questions. So now we get on to a bit on low and zero emissions. So I'll welcome our next speaker, Dr. Robert Cohan, who's a senior engineer at NTRO and who has extensive experience in electric vehicle and transport decarbonisation research, and will share his insights on EV developments in Australia and New Zealand. Robert's currently based out of our New Zealand office at the moment and been there for almost a year, coming up at towards the end of this year. So I'll pass over to you, Robert.
Yeah, thank you very much, David. For the introduction, I share my screen again, like the others did. And I hope you can see that.
Yeah,
know if you can't.
It's not in slideshow. It's in your just normal screen layout.
Oh, okay. I changed the slideshow then. Is that better?
You might have shared the wrong screen.
The wrong screen then? Okay. Not sure why this is not working the way it should.
Could you unshare? Maybe stop sharing and then reshare.
Robert, you can access the monitors. So again, go full screen.
Go share again. Oh, full screen again, yeah.
Yes.
And then
at the top, you see display settings. Just click on that small icon. Display settings at the top.
Display settings, yeah.
Yes.
Swap.
And then swap. Swap or yes.
All right.
Yeah.
Okay. Thank you very much.
Better. Thanks, Robert.
Cool.
Over to you.
Thank you. Great. So, yes, thank you for the introduction, David. I'm going to present a bit about the recent electric vehicle developments in Australia and New Zealand. That will be a bit of a different presentation to the other ones because it's not based on certain projects or certain initiatives that NTRO does it, but it's more of a general update in across the two countries of Australia and New Zealand and how they compare internationally in the electric vehicle uptake. I want to start with an overview of the whole world internationally, what EV sales look like. This is a figure from the International Energy Agency, and it shows in the darker the green is, the more electric vehicles were sold in the last year. There are some countries, especially China and some countries in Northern Europe, that are very far advanced, that have almost Norway close to 100% electric vehicle sales amongst the new vehicle sales. That is light vehicles, by the way, so cars and vans. And Australia and New Zealand, they are sitting not in top 10, not in top 20, a little bit below. So we still have some way to catch up internationally compared to other developed countries in the world. In general, like as a high level overview or summary of it, Australia, for Australia, the electric vehicle sales and model availability has definitely changed in the last years. There's more vehicles becoming available. But also the infrastructure is growing strongly, but there's still a need to develop more of the infrastructure. And the uptake of electric vehicles is not at the level yet where that it is needed for meeting our emission reduction targets. Many electric car models are also and more electric truck models become available in addition to cars, but especially for trucks, charging infrastructure and the cost and payload constraints or road access remain an issue that needs to be solved in the future. For New Zealand, they had a very strong uptake of electric vehicles a few years ago, but then due to policy change, that dropped a bit. But it's now growing again in recent times, probably also triggered by the recent fuel price changes that contributed to it. And they invest a lot into the vehicle-to-grid or vehicle-to-infrastructure initiatives and investments and research, and also into electric bus depots and truck charging demonstrations. So looking forward, it's less about the number of vehicles available or the model choice available. It's more about the infrastructure that needs to be developed and how the electric vehicles can be charged, both in depots or at home and as well as on the road. Policy needs to support that, and the heavy electric vehicles need to be supported so that they can drive on the roads without running out of charge. That's a very high-level overview. I want to go into some more details about both Australia and New Zealand in the next few slides. And I'm starting with Australia. As I mentioned before, light electric vehicles have grown strongly. There's a vast range of models available now, a lot of them from Asia, from China, that have come into the country. Most of them are fully battery electric vehicles, not so much a plug-in hybrid electric vehicles, although both of these options are available. There are currently about 153 models available. So you see that in the right box and the blue box with a few numbers and details. I don't want to go too much into the details in each of these, but in summary, we have had a strong growth recently with electric vehicle sales. We were at 12% of new car sales about in the first half of 2025. That has then grown to 20% of new car sales in the last quarter this year. We had last year about 400,000 electric vehicles on the roads. That has probably grown by now again, maybe closer to 500,000, 150 different car models, and also the plug-in hybrids have grown strongly. When we look at the infrastructure, and that's probably more of an area that needs to be developed further to enable wide adoption of all of these vehicles. The charging network is definitely growing, but there's probably a need to manage the data and the planning of the infrastructure a bit more. And that is both for the fast charging network, so the high power charging, like the picture on the below, and the middle picture, the slow charging network as well. Australia had about 1,200 high power charging locations as of mid last year, with a total of about 4,000 charging plugs across all of these locations. Again, that's a significant increase year on year. The rollout is shifting from adding more chargers to existing locations, rather than adding more different locations to the network. Also, the Electric Vehicle Council has taken the initiative for launching an app or a website called Charge at Large, which combines the charging locations of several different charge point operators. Across 2,000 different charging units across the country, across all of Australia, which brings together some of the data. But probably it's not yet enough. There needs to be done more in terms of data management. So it says there's a lack of single complete sort of truth for charging infrastructure data, which is needed for more consumer confidence and for the planning and rollout of the network, also in relation to managing the grid, so that there's enough capacity in the electricity grid to support all of these charges. And that's also for heavy vehicles that I'm talking about a bit later, because they have higher charging power demands. Heavy vehicles, they are, compared to light vehicles, they are emerging. So there are not as many different models or options around yet. And they are probably more constrained by logistics and operational requirements than the light vehicles are. But definitely the options are growing. You can see on the left, we have even heavier vehicles, we have buses, we have waste collection vehicles. All of them have electric options available. The big challenge is the heavy vehicle charging infrastructure, especially the charging infrastructure outside depots, which is not existing essentially at the moment in Australia. So for longer distances, operating these vehicles becomes a bit of a challenge unless you return to a depot and have a charging location there. Yeah, but again, model availability is increasing both for the heavy vehicles and also for the commercial vehicles, the vans and utes. But Australia truck sales are still behind other countries. We have New Zealand where it's 4.8% compared to the 0.3% in Australia, and all the other countries, China, Norway, are further ahead. Zero emission buses. There's also a lot of investments into new electric bus depots, fully electric buses that are converted or being built or invested into. But yeah, as I said before, the heavy vehicle charging infrastructure is a major gap, which puts a bit of a brake on the uptake of these vehicles, especially for certain applications for longer distances. So in summary, we need to keep the policy support through a bit longer. This is a recommendation from the Electric Vehicle Council until we have about 30% electric vehicle sales penetration to keep the momentum, to keep going towards the amount of electric vehicles we need to meet emission reduction targets. Electric vehicle uptake is not yet enough to match emission reduction pathway. There's an increase needed of 50% plus by 2030. We need to build a national heavy vehicle charging roadmap to enable more heavy electric vehicles come on the road and contribute to the emissions reduction targets, as well as more public charging and grid capacity analysis integration with the electricity grid to make sure that the high power demands for heavy electric vehicles are met and catered for. We need to address some of the costs for heavy vehicles. That's upfront cost charging, dedicated charging spaces, payload penalties. If you consider that currently heavy electric vehicles are usually heavier than the comparative petrol diesel variants. So that needs to be considered as well. And the vehicle to grid or vehicle to infrastructure communication needs to be looked at because these heavy vehicles have bigger batteries that can be used as energy storage devices as well in the future grid network. Now, over to New Zealand. It's similar, but also a little bit different. We have had a rebound of electric vehicle uptake after some policy changes. So New Zealand has had a history of strong electric vehicle support earlier on, 2020 to 2023 maybe. And then the government changed and policies changed, which means they ended the discount on the sales of electric vehicles and at the same time introduced road user charging for electric vehicles. And that brought down the number of new vehicles being sold. But recently that has changed again, also probably driven by the fuel prices, the high fuel prices. So electric vehicle sales has increased again. Also, New Zealand has some strong government-backed investments into electric vehicle infrastructure. So they're supporting the rollout of new public chargers across all of New Zealand. They have currently about 1,800 charge points. They have investments into ChargeIt in Meridian. That's a charging network operator and an electricity company to roll out many more chargers over the next few years with a $52 million zero interest loans. The planning rules were also changed for electric vehicle charging infrastructure that they consented faster under nationally consistent permitted activity rules. New Zealand plans to have charging infrastructure every 150 to 200 kilometers across the main highways or across all of the country. And they, as I said earlier on, they're investing a lot into vehicle to grid or vehicle to infrastructure initiatives, research initiatives to see how electric vehicles can function as an energy storage device in the electricity network. When we look at heavy electric vehicles in New Zealand, it's probably a bit similar to Australia as well, although they have a bit of a greater uptake as of now. New Zealand is made it or trying to make it easier for reducing rollout barriers for heavy electric vehicles, and again their investment and research into heavy electric vehicle infrastructure. They have the road user charge that they have implemented in in New Zealand does not apply to heavy electric vehicles yet until mid next year, July 2027. So there's a bit of an incentive there. They're investing a lot into electric bus depots. For example, here in Wellington, where I'm based at the moment, they are building a new electric bus depot right near the airport, which will be fully electric for the electric buses that you can see in the pictures below here in Wellington. And the New Zealand Energy Efficiency and Conservation Authority is behind a lot of these investments, driving the research and putting out tenders to invest into heavy vehicle research and demonstration projects. So in summary, there is a plan to deliver 2,500 plus more charge points quickly and reliably across all of New Zealand, with a progress towards more than 10,000 by 2030, which includes all of the rural highway gaps that need to be closed so that there will be enough charging infrastructure every 150 to 200 kilometers. This scale of electric vehicle charging beyond demonstration. So they want to scale up the heavy electric vehicle network, make megawatt charging, so very high power charging hubs possible. That's what the tenders and Energy Efficiency Authority funding is for. They want to maintain the market momentum after the double disincentive that I mentioned earlier on, with the discontinuation of the incentive, the discount, and the introduction of the electric vehicle road user charge. So they want to sell more of these, and they're investigating vehicle-to-grid and vehicle infrastructure research initiatives. Right, so that was a brief overview of Australia and New Zealand, where we're at the moment in terms of electric vehicle uptake, electric vehicle needs, what we need to look at in the future. And NTRO has done quite a few projects in that space on different aspects in the past. Most recently, we have been looking at the project on the Australian new vehicle emission standard. New vehicle efficiency standard, sorry, the second point here on this slide, where we looked at different points of compliance of that standard. That standard came in effect in Australia at the beginning of last year, and our recommendations will be considered for future revisions of this standard. We also did a market analysis for a local council in Australia to look at the different options for low and zero emission base collection vehicles, to advise them what the market has to offer at the moment, what the challenges are, what they could consider for replacing their fleet in the future. We did further to that national work at an Austroads level, where we looked at similar signage for electric vehicles, the project that I led, and different works for private organizations and state governments as well. So with that, I think that's enough of an overview for now. Thank you very much for listening, and back to David.
Great. Thank you very much, Dr. Robert Cohan, and he'll be available at the end for any questions that people might have. Yeah, so now we're up to our last speaker, but certainly not least. Last but not least. So I'll please welcome Dr. Hendrik Zerlinden. So he's a principal engineer at NTRO, who specialises in motorway operations and traffic flow theory, research and implementation, and will share his insights on improved capacity guidance for motorways in Australia and New Zealand. So over to you.
Yeah, thanks, David. Can you see everything?
I might still be sharing. No?
Am I sharing?
Yes.
Yeah. Okay.
You're all good.
Okay, very good.
I'll stop
No,
sharing.
thank you. So, I'm going to talk a bit about improved capacity guidance for motorways in Australia and New Zealand. And This is also a bit different to the previous presentations because we are now back in the world of good old traffic engineering, I'm tempted to say. And no matter whether you'll have automated vehicles or electrical vehicles, this is still required that you need to understand capacity as well as demand. And I will probably spend as much time on why we need that to do that research as on the details. So trying not to confuse you. So yeah, why is capacity guidance important? And why isn't it available yet? So yeah, capacity, or how we call it these days, maximum sustainable flow rates, to distinguish it a bit from the old concept in the US Highway Capacity Manual. So capacity must be greater than the traffic demand everywhere along a motorway corridor. And when you look at that diagram in the top right corner, so capacity or maximum sustainable flow rate is illustrated by the green or red lines. And you see the motorway corridor from left to right, or now the other way around, from right to left. And traffic demand or flow is illustrated by the columns. And I think it's pretty logical that you need to have greater capacity than traffic demand everywhere along the corridor, even if you only have one short section, such as a weaving area with crossing traffic streams where capacity is lower, then you have a really significant problem. So the green line is meant to illustrate a situation where capacity is always slightly higher than the demand, represented by the columns, and the red line is when you haven't done such a good planning. Yeah, so the relation between capacity and traffic demand or flow must be in balance. And if we don't understand capacity, there's a risk that we build strong bottlenecks into the motorway network, and then you might even have recurrent congestion everywhere, and that can spread very quickly. And what is important to understand is that it's not only delays that it causes, also the crash rate goes up 5-fold if you're in congestion, roughly, of course, and emissions increase and so on. So, and some planning disasters, how I've a bit provocatively called it here, have happened in Australia in the past. And I'm giving here the Rozelle interchange in the Sydney area as an example. I don't know exactly why that happened, but if you have really good guidance, then you can at least lower the risk. This is the absolute minimum that you need to have. The other thing that I'm trying to show here again, trying not to overwhelm you a little bit. So understanding capacity is also essential when operating traffic management system, such as ramp metering, with the underlying Alinea Hero ramp metering algorithm. That's how it's called. At least in Victoria, this is used, and in Western Australia, where I'm now. And yeah, ramp metering, you know that there are simply traffic signals that control the access so that you don't exceed the capacity of the roadway. And you need to understand capacity in order to decide at what traffic level do you need to start up the system, or what is the target flow rate, for example. And that's what I'm trying to show here. I've tried to neutralize it a little bit so that you don't see where exactly it is, or it's in part IP protected. The numbers are a bit small here. Sorry about that. So, but you need to enter the capacity, and you need to enter a fixed critical occupancy, or the target occupancy, which is comparable to the density, the target density, as the number of vehicles per kilometer. And everything that I'm presenting now based on capacity as a certain sustainable flow rate is also transferable to the concept of density, traffic density. So surprisingly, or maybe surprised you that there's still significant gaps that were identified in Austroad's capacity guidance, such as the Austroad's Guide to Traffic Management, which I'm showing here, and also the Guide to Smart Motorways, and we are trying to help closing that. So yeah, this is a bit wordy. I'm trying again not to overwhelm you. But I'm talking a little bit about the project that we are working on, Austroad's NEG 6527, which is the capacity update of the Austroad's Guide to Traffic Management. Current Austroads and US Highway Capacity Manual capacity values are often not sustainable. This means you can operate a motorway at a certain level for a short time, but not over an entire peak period, which may be 3 hours. Another weakness in the US highway capacity manual is that it assumes that capacity is always, per lane capacity is always the same, no matter if you have a 3-lane or an 8-lane US freeway. And that's simply unrealistic. I will explain it a little bit based on this diagram, which most of you will probably be familiar with, more or less. So this is a classical speed flow curve. And when you have low flow, you start at a speed that is close to the speed limit, and then when you increase the volume, then it goes down. And this point here, the apex, has been assumed as a good capacity traditionally. We know when you operate here, then you have a very high chance of congestion in an entire peak period. That's why we think you need to go a bit lower, and that's why the Victorian Motorway Capacity Guide defines this capacity or maximum sustainable flow rate. It links it to a certain flow breakdown risk, which is 1% per 15 minutes or 10% per 3 hours. And this is shown here by that red dotted line. And this point, or that line coincides with the highest productivity, where productivity is a bit of an artificial construct. It's simply the combination of speed and flow, or the mathematical product, where flow represents a good operator optimum. You want to have good infrastructure utilization, and speed is a user optimum, high speed. So these points coincide. That's probably the most complex bit I'm going to go through during this presentation, but this is what we are doing now is based on. And that object, we want to provide member agencies with clear guidance to apply these concepts, such as the flow breakdown risk concept or maximum sustainable flow rate concept, and the flow rate at maximum productivity. And just a bit of an overview. We are in the middle of that project. What we've been doing. So it's quite, you have all the classical tasks that you normally do: stakeholder consultation, key references. We have collected data from 67 bottlenecks, long-term data, because you have all these random fluctuations as well. We have developed a methodology to divide an entire freeway/motorway network into segment types, because you have different segments, which I'm going to talk a little bit about. And the core is really the capacity performance curves that typical capacity performance curves, such as flow breakdown risk curves. That's what we have already delivered. And currently, we have also given them a detailed description of how you develop your own curves. Very briefly, so it's interesting that some of the past capacity guides, in my view, were a bit too complicated. For example, the HGM, it distinguishes between merge areas, basic areas, and diverge areas, where it's suspected that merge areas have lower capacity than the other ones. We couldn't see that. That's why here we have persuaded or convinced the project control group that it is enough to have standard sections and come up with typical capacity curves for these standard sections. So decreasing complexity was one achievement already. So what we have given them already is for the multitude of different conditions, such as smart motorways, which have higher capacity, versus unmanaged motorways. Smart motorways characterized by rent metering, extended rent metering. So we have provided capacity guidance for smart motorways versus unmanaged motorways, for different gradients, because steeper roads have lower capacity, for different heavy vehicle percentages, because the more trucks you have, the lower the capacity is. So in short, for all these combinations, we have provided such flow breakdown risk curves where at a certain flow rate, you have a certain flow breakdown risk. And also we have provided tables for some points along this curve. For example, this point here is the 1% flow breakdown risk per 50 minutes or 10% over 3 hours. We have provided tables depending on gradient and heavy vehicle percentages, and the corresponding flow rates, so that jurisdictions can design the motorways. So this is a one project, and what we have identified is, I've shown this earlier. So you have one really interesting segment type are weaving areas, where you have strong crossing traffic streams, and this produces lower capacity. But there was a clear gap that the US highway capacity manual methodology for assessing weaving areas, many people have commented the results are all over the place. And there's nothing better in the Austroads guide, and that's why I've also worked on this WARRIP project, weaving area capacity analysis. I'm briefly going to talk about what we have done. So we have invested 12 weaving areas where you have strong crossing streams in Western Australia and in Victoria. For example, on the Kwinana-Mitchell freeways here. We have measured speed, volume, and occupancy, which is routinely measured by in-pavement detectors to come up with the capacity curves or flow breakdown risk curves. We have also measured lane changing data, and that is probably would be a lecture in itself. How do you do that? You can do automated number plate recognition at adjacent bridges and compare where in which lane was a vehicle, and then based on this you can calculate the lane changes per hour. But there is also a new type of what we call advanced freeway data stations, so-called turtle detectors that can re-identify vehicles at adjacent detector sites, and that is shown here as a schematic scheme and also as a photo from the Monash Freeway. So they can re-identify vehicles at adjacent detector sites 500 meters apart, including the lateral position, including the lane that they were in. And what it sounds complicated, but in the end, what we have simply done, we have found a functional relationship between the lane changing concentration, number of lane changes per vehicle per kilometer, and the capacity loss compared to typical conditions, and that is shown here. So sort of spelled it out here. So this is the lane changing concentration, again in a number of lane changes per kilometer per vehicle. And this is the residual capacity or residual maximum sustainable flow rate. And the higher the lane changing concentration, the lower the capacity, and seems to be plateauing. So a very simple methodology, we believe quite robust. And when you want to apply it, you simply take the estimated lane changing concentration, go into that curve, define a weaving factor, and then you can multiply that weaving factor by the base capacity. Yeah, so hope I'm not going over time. So in the end, you have to estimate the lane changing concentration. For example, for this section where you have an auxiliary lane, you simply multiply the vehicles that have to progress from the ramp to the freeway to the number of vehicles that have to progress from the freeway to the ramp. They are crossing path, and by doing that, reduce capacity. Sum it up, divided by 2.08 by the weaving area length and by the number of vehicles, and then you have the lane changing concentration as an input parameter to that. Can probably skip that. And so this is then this WARRIP project feeds very nicely into that Austroads project that we are doing, and we can then use it in the end to provide updated guidance for the guide to Austroads guide to traffic management. That's what we are working on. We have developed that for Western Australia and for Victoria, but we are currently also applying the new methodology to Queensland weaving areas and New Zealand weaving areas. So yeah, that is already the end of the presentation. There's obviously a lot more that I could talk about, including all the technical details. But this is really was meant to show you that yeah, we are also working on these more classical things than the nice things like automated vehicles and so on, artificial intelligence, electric vehicles, and so on. Thank you.
Great. Thank you, Dr. Hendrik Linden. So now is an opportunity for questions. Yeah, so just while people are thinking up their questions, I guess just to kind of wrap it up, I guess what we're seeing today is just how broad and rapidly evolving, I guess, the transport future space has become, from next generation weigh motion systems and advanced analytics to automated vehicles, managed motorways, and low emission transport. I think, yeah, really the common theme here is leveraging emerging technologies and new ways of thinking to address future transport challenges and improve the movement of people and goods. So yeah, well, we don't necessarily have any questions, or maybe we do. Ali, have you got a question?
We had actually lots of questions and I forgot to write them down. And now I'm thinking, okay, what was my question for the first and second and the third? So apologies, my thoughts are a bit scattered. Well, interesting and very exciting research projects at NTRO. So I'm a very proud ex-NTRO employee. I had a few questions regarding the automated bus pilot, which is again very exciting, very unique projects that only organizations like NTRO is able to lead here in Australia. I was wondering whether you had permission to operate it on public roads, or you just basically are operating in like I don't know, test areas provided by Transport for New South Wales or the other organizations, or can you actually operate it on public roads?
Are you on mute, Ronnie?
Hello, can you hear me now?
I can hear you now. Yeah.
Okay, sorry. Yeah, I was saying that we cannot go on public roads yet, Ali, but we're working towards that. So when the vehicle arrives, we need to get it sort of, approved for entry into Australia, and then we have to get it registered. So that paperwork is still being sorted out. It can now operate under private premises. But yeah, we're working towards operating these on public roads. As I said before, this particular bus and technology is actually being trialed on public roads in Japan. So I don't see any reason why we cannot work towards that, working on public roads.
Okay, thank you. Let's see if there's any other questions. I have a few questions, but
yeah, we have some backup questions, but go fire away, Ali.
But I see one question here by Dr. Misbah from Amicab University. Dr. Misbah, you can actually, I think, unmute yourself and ask a question. Or David, you can read the question for Hendrik.
Yeah, no worries. So the question is, Hendrik, is there a cap on the length of the weaving area in the proposed method? Question. And then a bit of clarification. Oh, there's two questions. Yeah, so that's the first one. Yeah. So maybe I asked that one. Yeah.
I'll start with that one.
Yeah.
No, thanks very much for the question. I think it's a good one, and I believe you're coming from the US Highway Capacity Manual that defines a maximum length over which a maximum assumed length over which weaving might exist. So the short answer is no, there's no limitation in the methodology, because we are talking about the lane change in concentration, which is lane changes per kilometer. And when you extend the weaving area length to, say, 3 kilometers or 4 kilometers, then the lane change in concentration gets very low. And then also the base capacity reduction gets very low. So in the end, it's something that we didn't need to define an artificial threshold value for the weaving area length, because I've said it already. When you really extend the weaving area length to very long length, then you have very long assumed influence.
Yeah. So the clarification around that, it might be a separate question or might be another one, but he's saying, how do you differentiate between a merge, diverge, normal segment and a weaving segment?
Yeah, so in the end, we have decided that we don't have to distinguish between merge, basic, and diverge sections, because we couldn't, at least based on the sites, on the data that we had, we couldn't measure a significant influence of merging. So that problem is a little bit solved in a way. Weaving areas is simply where you have crossing traffic streams. For example, where you have a lane drop. If you do the drawing, or where you have a lane drop or a lane add or an auxiliary lane, which is both a lane add and a lane drop, then you automatically have traffic streams that must cross. So we defined that based on the geometrical conditions in the end. For the merge areas, I know that the highway capacity manual has some influence areas for the merging, but this is artificial in a sense. And but like I said already, in our proposed methodology, we don't have to distinguish between merge, basic, and diverge, and that is, for example, what the Dutch are doing as well, and also the WIG-DTP motorway capacity guide. Apologies for the a bit lengthy answer.
That's okay. Thank you, Hendrik. Did you have any questions, Ali, for the other speakers?
Yes, actually, I had a very similar question from Henrik regarding the capacity estimation. First of all, my understanding was that all of the road agencies, once that they are planning for building the highway, all of those on-ramps, off-ramps, etc., they do estimate these capacities for expressways using exactly the fundamental traffic diagram. So very kind of like similar approach. My understanding was that they already provide the capacity. Could you elaborate more that this guideline that you are developing for Austroads, actually what was missing that you are trying to address or harmonize for the road agencies?
Yeah. Look, you're coming from the classical speed flow diagram and from the apex, and then what has been done in the past was take this highest value, highest flow, and some countries then multiply that by 0.9 or something, take 90% that for design as a design value, but that is a bit arbitrary, and that's why we think that these flow breakdown risk curves are a better approach, and because you can see what you get. And that is one fundamental difference. So in the end, WIG-DTP wasn't happy with the old HCM approach because, like I said, it underestimated a little bit, overestimated capacity, and that's why they developed their motorway capacity guide based on this flow breakdown risk concept and the max productivity concept. So this is the one thing, and the other thing is really the weaving area capacity analysis methodology, which was in the US HCM for decades. And everyone knows, and you find it in literature everywhere, it is really, you get results that are all over the place, not. And that's why we wanted to develop something that is not 100% correct, but robust. And that led to this curve that I've shown you. So you don't have the risk that you, for example, in your model produce negative speeds, as is the case with a newly proposed US HCM one. We wanted to produce something robust and reasonable for practitioners. Yeah, and we have submitted an article for TRB, and we'll see what they think about it.
Yeah, quite useful. Thank you. Maybe again, the question that Dr. Mesbah asked also made me thinking that basically the ramp influenced area is kind of very uncertain for myself. My research focus is not really in traffic engineering, and I had a student who was basically looking at the lane changing behavior and gap acceptance behavior when we have a dedicated lane for autonomous vehicles, and we have a platoon of trucks, automated trucks, and then we have on-ramp and off-ramp, and the different distances between on-ramp and off-ramps, and also the start and end segment of the dedicated lane, how basically these are all interacting with each other, and how these basically attributes impact the lane changing behavior in the ramp influence area. And I looked at actually the literature is a bit gray gray area that how do we really define that ramp influence area? So basically, again, reflecting back on what Dr. Misbah asked about the length of the weaving area, and you mentioned about the density, etc. So if you come up with any findings or any suggestion that how we can certainly identify the ramp influence area, I would really be keen on learning that.
If I can add to that, that is something where the research is probably not complete what we are doing, because we have only looked at so many merge areas, and we are NTRO. We are always asking for more work, more meaningful work, and we have proposed a project on merge area and diverge area capacity, where you have really strong merging movements and strong diverging movements. That is still a little bit of a gap, because they wanted us to do everything, and you can't do everything in detail. And with that weaving, we believe we have done really a good, at least a thorough job, because we had a separate project on the side. With merging, diverging, there's probably still a bit more work to be done. But so far we couldn't see any really strong influence of merging and diverging for moderate merge and diverge levels.
Okay, thank you, Henrik. To not really dominate the chat, I will just
sorry.
myself.
Yeah, we've got a question for Kenneth. Able to turn on your camera and audio. So Kenneth, can you please explain why is it hard to extrapolate the virtual wave motion? Kenneth, are you on? Yeah.
Yep, online. So in terms of extrapolating the virtual wave motion, for the general vehicle, I'd say it would be pretty hard to extrapolate the mass, more for the fact that the footprints of the vehicles that operate on the network, your standard car, there's a lot of them that operate. They've got very similar footprints. So the spacing between the axles, the width of the axles, and if you try and compare them, they're not really going to be able to get an insight on where they're operating their mass. These vehicles themselves, there's a bit of a difference between the mass that they putting onto the pavement, but they're also not necessarily as much loading on the structures as the larger, heavier vehicles. The vehicles that we looked at as part of the project were more the class 1 oversize over mass, so the low loaders, the load platforms. They're pretty easy to distinguish in the fact that they have 5+ axles on the trailer. They're carrying pretty large loads, which may damage the infrastructure. And you're less likely to have a larger amount, or you're less likely to have lots of those vehicles running around the network. So extrapolating the mass from those is it's important to see where they're operating, how they're operating, and understand if they're going over bridges that may or may not have been designed to allow these vehicles to operate. So hopefully that sort of covers a bit of why it may be easy or hard to extrapolate virtual wave motion.
I guess another question on that, Kenneth, sorry, is why do we need WIM when there are vehicles with onboard mass on a network?
Well, I suppose each of those technologies have different purposes. So they're operated potentially by different organizations. So onboard mass, they they may be required through levers which are utilized so they can access the network, but the transport agencies may not actually get access to the onboard mass data that I believe goes directly to the NHVR, although I do understand that there will be some provisos in the new sort of legislation, or not legislation, the new schemes such as what's going to be happening in Queensland. Sorry, having a mental blank on what the scheme is, but where it improves the ability for the larger vehicles to get their permits approved with the access to the network. So they each provide different information, but what would be sort of better is if you can get both of those information. So the weighing motion is at one site, which captures all the vehicles running over that location, all the axle masses, and provides good detail at that one location. But it doesn't provide the whole network or where those vehicles are operating. If you can combine them together, it would allow for things like calibrating of the weighing motion site, allow for extrapolating the mass from that site to another site, or another classifier site. The world's your oyster.
Yeah, great. Well, thanks for providing a very detailed answer, Kenneth. Much appreciated. A bit of a question for Robert. What is the future for heavy vehicles, battery electric or alternative options such as hydrogen or renewable fuels?
Yeah, thanks, David. So, while in the past we have, or NTRO has done research into both electric ones and hydrogen options, but recent research has shown, or developments have shown that for all off-road transport, both light and heavy vehicles, they will most likely be electric, so fully battery electric, not hydrogen or other options. In the short term, there may be use cases for alternative fuels. We're talking hydrogenated vegetable oil, which is HVO, or renewable diesel essentially for trucks, which obviously has a lower emission impact compared to fossil diesel. The problem is that there is not enough of that in Australia at the moment. It's also imported, which creates additional emissions, and it's also relatively expensive because of the limited supply of it. But in the long term, what the market says, also what we see internationally, is that all road transport will most likely be electric. It's just the most efficient option, and there's just a bit more of battery technology that needs to be evolve for heavy electric vehicles to become a little cheaper than they are at the moment. Also, maybe a little lighter than they are at the moment. Yeah.
Great. Thank you, Robert. I got a question for Safa, if you're online.
Yes.
Yeah, good on you. Yeah, so how can new data-driven approaches be embedded into day-to-day practice?
So David, from what I saw, especially from practitioner point of view, there is an ecosystem that like usually adopted in any organizations. So they have a normal way of operating things, like look at the traffic flow, look at the safety, look at like the infrastructure, routine inspections. And when we define a new approach, new source of data, new analysis, sometimes they can be contradictory. with the current normal work that they are doing. So the very first step is validating the new approach against the current practice, and also providing an environment that both kind of approach can work together in parallel, and then the practitioner get used to the new approach. It happened to me, for example, that I tried to replace a machine learning, like the regression model with a machine learning model. And the question was how we can understand it, because it's not equations like what we used before, which is true. And that's reasonable because it's not a normal practice. But it getting like we need to spend time and also develop in parallel with the current like the workflow that they have, and also organizations who do the certification and do the comparison. So for example, what we see in terms of guidelines that, for example, ASTROS provides, or NTRO do that type of certification as well. This is an opportunity to showcase that what are the alternative ways of current practice. So it helps to adopt this type of new approach.
Yeah, great. Thank you for your answer.
Thank
Very
you.
much appreciated. Back to Ronnie and the automated driving bus. What are some examples of the immediate use cases that you can think of?
Given that we've so far only been testing in the closed environment, I think the more immediate use cases were probably within precincts in a more controlled environment, such as campus environment or airports environment. So those kind of use cases are probably the more immediate ones. Yeah, having said that, we're working towards public roads use cases, but that will probably can come a bit later.
Yeah,
that makes sense.
Yeah. Good. Thanks, Ronnie. Probably got time for one more question, so maybe we'll go back to Hendrik. What practical consequences will the new capacity guidance have for standard motorway segments and for weaving areas?
Yeah, maybe starting with weaving areas. So in the end, you have increased transparency around the impact of different weaving and different weaving design on capacity. And when you find that you have the planned capacity is lower than the planned demand that comes from a traffic model, then you need to do something about capacity, and you can increase it, for example, by extending the weaving area length. So back to the lane changing concentration, it's lane changes per kilometer. If you increase the weaving area length, then you reduce the lane changing concentration, and then you reduce the capacity decreasing effect of weaving in the end. Yeah, but it's just one scenario. Or you can work on maybe trying to reduce the amount of weaving traffic by different design of an entry ramp, where you could, for example, have a 2-lane entry ramp where the inner, I wish I had a drawing now, where the vehicles entering via the inner entry lane don't cross path with the exiting vehicles.
Yeah.
Something like this. I'm making this up on a little bit. Yeah. So in the end, you can, you know how you can, you know how you can increase capacity in a way, or you understand better the relation between capacity and demand, then you get a better, you avoid under or over dimensioning your infrastructure. Under dimensioning means you build a bottleneck into your network, and over dimensioning is you spend too much money on the infrastructure.
Great. Well, thank you, Hendrik. So unless there's doesn't look like there's any last minute questions, so we'll finish up around now. As you can see, on your screen, we've got all our contact emails if you want to reach out to us, so please do. But yeah, as you can see, the work that we do in Transport Futures is really quite cutting edge, and it ranges from looking into ITS and established practices and traffic engineering and how that can be brought into the modern world, even through like Hendrik's work with capacity flow theory and Kenneth's work on WIM and how that can be enhanced with further data integration. Then you've got Sepa's work looking at AI and advanced analytics, and then of course Ronnie's and Robert's work on the automated driving bus technologies, and then transitioning to low and zero emissions. So the work we're doing has evolved, and I think no doubt will continue to evolve going forward. So if you do have any questions for us, please reach out to us on the email. But apart from that, hope you enjoy the rest of the Bridging Transportation Research Conference. And of course, on that, thank you, Ali and her colleagues for putting the conference together and giving us the opportunity to present at this special information session. So much appreciated, and hope you enjoy the rest of the conference.
Thank you. Thanks, David, and thanks, everyone.
Thanks, David.
Okay. Thank you, everyone.
Thank you, everyone.
Thanks.
Thank you.
Thank you.
See you. Bye. Bye.